We thought we knew the size of everything. 93 billion light-years across, horizon to horizon, a sphere of galaxies and stars and empty space that we mapped, measured and called complete. We built telescopes powerful enough to see the afterglow of creation itself. We traced the expansion of the cosmos back to its first violent second. We convinced ourselves that the observable universe was not just what we could see, but all there was to see. And then the numbers stopped making sense. Galaxy clusters are moving, not drifting, not expanding with the universe the way they should. They are being pulled. Something beyond the edge of everything we can observe is dragging material across billions of light years at 2 million miles per hour. We do not know what it is, we cannot see it, but the motion is there, recorded in the data, undeniable and unexplained. And that is just one problem, because when you ask physicists what lies beyond the cosmic horizon, beyond the farthest light that will ever reach Earth, you do not get one answer. You get 8. 8 competing theories, each more unsettling than the last. True nothingness, where even the concept of space ceases to exist. An infinite multiverse with 10 to the 500th power variations of reality, most of them utterly hostile to life. Hidden dimensions stacked beyond our perception, where entire universes might be layered just millimeters away. And then there is the theory that makes every other question irrelevant. The one that suggests none of this is real at all. In the next 30 minutes, we are going to walk through every major hypothesis science has produced about what exists outside our universe. Some of them are strange, some of them are beautiful, and one of them will change the way you think about everything. This is that journey. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We need to talk about the edge of the universe, not because anyone has seen it, not because we've sent a probe there or mapped its coordinates, but because the moment you try to picture where the universe ends, your brain does something strange. It tries to imagine what's on the other side. And that question, that simple human impulse to ask what comes next, has turned out to be one of the hardest problems in all of science. The observable universe is 93 billion light-years across. That number gets thrown around a lot in documentaries and articles, usually with some dramatic music and a slow zoom through a star field. Most people hear it and nod along because the number is so large it stops meaning anything. 93 billion light-years. Your brain can't hold a number that size. It just files it under big and moves on. But let's not move on yet, because that number, the one everyone uses to describe the scale of everything we can see, is hiding something important. The universe is not 93 billion years old, it's 8 billion years old. So why is the observable universe 93 billion light-years wide instead of 6 billion, which is what you'd get if you just doubled the age and assumed light traveled in a straight line outward from the Big Bang? The answer is that space itself has been expanding the entire time that light was traveling toward us. A photon that left a distant galaxy 13 billion years ago didn't just cross a fixed distance, it crossed a distance that was stretching beneath it the whole way, like running on a treadmill where someone keeps turning up the speed. By the time that photon reaches our telescopes, the galaxy it came from has been carried much farther away by the expansion of space itself. The present distance to that galaxy, accounting for all the expansion that happened while the light was in transit, works out to roughly 46 billion light-years in one direction. Double that and you get the diameter. 93 billion light-years. That's the observable universe. Not the universe, the observable universe. The part we can in principle see because light from it has had enough time to reach us since everything began. It is the patch of cosmos contained within our cosmic horizon, the boundary beyond which light has not yet had time to arrive. Here's the thing nobody tells you when they first explain this. The observable universe is getting bigger, right now. Not because the universe itself is necessarily getting larger, though it is, but because with every passing second, light from slightly more distant regions finally completes its journey to Earth. The horizon isn't a wall, it's a wavefront, expanding outward at the speed of light, pulling more and more of the cosmos into view. Every day, the observable universe grows by about 2 light days in radius. You will never notice this. No telescope will register the shift in a human lifetime. But it's happening. The universe you can see tomorrow is fractionally larger than the one you can see today. A light year is not a unit of time. This trips people up constantly, and it's worth pausing to fix it now before we go any further. A light year is a measure of distance. It's the distance light travels in 1 year, moving at roughly 300,000 kilometers per second through empty space. 1 light year works out to about 9.46 trillion kilometers. When astronomers say a galaxy is 10 billion light years away, they mean the light we're seeing left that galaxy 10 billion years ago and has been traveling ever since. We are looking backward in time. The farther out we look, the further into the past we see. This is why cosmology is an unusual science. You can't run experiments on the early universe. You can't rewind it or poke it with instruments. All you can do is look out, which is the same as looking back, and try to piece together what happened from the light that managed to reach you. Every photon is a fossil. Every spectrum is a clue. The universe has been writing its own history in light for 13.8 billion years, and we're standing here at the end of the story trying to read the first page. The cosmic horizon is the practical limit of that reading. It marks the boundary beyond which no information can reach us, not because something is blocking it, but because there hasn't been enough time. Light moves fast, but the universe is old, and space is big. And those 3 facts conspire to create a hard edge to what we can ever hope to observe. Anything beyond that edge is not invisible because it's dark or hidden. It's invisible because its light is still on the way and will not arrive for billions of years, or, in many cases, will never arrive at all because the expansion of space is carrying it away from us faster than light can close the gap. That last part is worth sitting with for a moment. There are regions of space moving away from us faster than the speed of light. Not because anything is violating Einstein's rule that nothing can move through space faster than light, but because space itself is expanding and there's no speed limit on that. A galaxy can sit perfectly still in its local patch of space, while the space between us and that galaxy stretches fast enough that the distance grows faster than light can cross it. Once a galaxy crosses that threshold, it's gone. We will never see it. Any light it emits in our direction will spend eternity trying to reach us and failing, like a swimmer fighting a current that's too strong. The Big Bang is not an explosion. This is another thing that gets misunderstood early and then calcifies into the wrong mental picture. The Big Bang was not a fireball erupting into empty space. It was the event that created space itself, along with time, matter, energy, and everything else. There was no before in any meaningful sense because time as we understand it didn't exist yet. There was no outside because there was no space for an outside to be in. The Big Bang happened everywhere at once because everywhere was compressed into a single point of infinite density and temperature, and then that point expanded. The early universe was not a cloud of stars scattered across a dark void. It was a fog. For the first 380,000 years after the Big Bang, the universe was so hot that atoms couldn't hold together. Electrons and protons bounced around in a dense soup of plasma, and light couldn't travel more than a short distance before slamming into another particle and scattering. The universe was opaque, then it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Light could suddenly travel freely. The fog cleared. The universe became transparent, and the light that was released at that moment has been traveling through space ever since. We see it today as the cosmic microwave background, a faint glow of radiation coming from every direction at once, the afterglow of the moment the universe went from opaque to clear. That glow marks the edge of what we can see in the electromagnetic spectrum. We can't look past it with light because there was no free light before it. Anything earlier than 380,000 years after the Big Bang is hidden behind that wall of plasma. If we want to see further back, we need something other than photons. Gravitational waves, maybe, or neutrinos, particles that barely interact with matter and could in theory carry information from even earlier moments. But as of now, the cosmic microwave background is the oldest light in the universe, and it sets a fundamental limit on how far back in time we can look using telescopes. So when we say the observable universe is 93 billion light-years across, we're describing the radius of a sphere centered on Earth, extending outward to the distance that light could have traveled since the Big Bang, accounting for the expansion of space along the way. That sphere contains everything we can observe in principle. Every star, every galaxy, every quasar, every filament of gas, every black hole. Roughly 2 trillion galaxies by current estimates, each containing hundreds of billions of stars. Some estimates push that number higher. The deeper Webb looks, the more distant galaxies it finds that previous telescopes missed. And here's the uncomfortable part. That entire observable universe, that 93 billion light-year sphere containing 2 trillion galaxies, is almost certainly not everything. It's just the part we can see, the part where light has had time to reach us. Most cosmologists think the universe extends far beyond the cosmic horizon. How far, we don't know. It could be a little bit larger, it could be vastly larger, it could be infinite. There's no direct way to test this. By definition, anything beyond the observable universe is inaccessible to observation. We can't see it. We can't measure it. We can't send a probe there. The information is locked behind a horizon that no instrument can cross. What we can do is think about what the math and the physics tell us is likely, and the math, based on our best models of how the universe works, suggests pretty strongly that the universe doesn't just stop at the edge of what we can see. Space keeps going. Galaxies keep forming. Stars keep burning. All of it unobservable, forever beyond the reach of our telescopes, not because of some limitation in our technology, but because of the fundamental structure of space-time itself. Historical views of the universe's extent have shifted dramatically over the centuries. For most of human history, the cosmos was thought to be small and Earth-centered. The stars were lights fixed to a rotating sphere just beyond the planets. The entire universe fit inside a shell you could maybe walk to if the sphere would hold your weight. Then telescopes arrived and the scale exploded outward in stages. The stars turned out to be suns scattered at vast distances. The Milky Way turned out to be a galaxy, one of countless others. What looked like clouds of gas in early telescopes resolved into entire island universes millions of light-years away. In the early 20th century, astronomers still debated whether the universe was static and eternal, or if it had a beginning. The idea that the universe was expanding, that galaxies were moving away from each other, and that you could rewind that motion back to a hot, dense state, was controversial. Some scientists hated it. Fred Hoyle, one of the most brilliant astrophysicists of his generation, spent decades fighting against the Big Bang model, preferring instead a steady-state universe where new matter continuously formed to fill the gaps left by expansion. He lost that fight. The evidence piled up. The cosmic microwave background was discovered in 1964, and that was the end of the argument. The universe had a beginning, but a beginning of what? If the universe started 13.8 billion years ago, does that mean it's finite in size, or does it just mean the observable part is finite? Does the universe have an edge, and if so, what's on the other side of that edge? For a while, cosmologists assumed that if the universe was infinite, it had always been infinite, even at the moment of the Big Bang. Infinite density and infinite size compressed into an infinitely small point. The math allows it, even if the human brain doesn't. Then inflation came along. Inflation is a modification to the standard Big Bang model proposed in the early 1980s by Alan Guth and refined by André Linde, Paul Steinhardt, and others. It posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a brief period of exponential expansion, growing by a factor of at least 10 to the power of 26 in less than a trillionth of a second. That's not a typo. The universe doubled in size roughly 90 times in a span of time so short that light couldn't even cross the width of a proton. Inflation solves several problems that plagued the original Big Bang model. It explains why the universe looks so uniform in all directions. It explains why space appears flat on large scales. It explains why we don't see certain leftover particles, like magnetic monopoles, that the earlier model predicted should be everywhere. And critically, it suggests that what we call the observable universe is just a tiny patch of a much larger cosmos that inflated together but has since expanded so far beyond our horizon that we will never see most of it. If inflation is correct, and most cosmologists think it is, then the universe beyond the cosmic horizon is not some exotic other place. It's more of the same. More galaxies, more stars, more planets, more dust, all governed by the same physical laws, all made of the same kinds of particles, all expanding in the same way, just farther away than light can reach. The observable universe isn't special in any cosmic sense. It's just the part we happen to be able to see from where we're standing. That should be a humbling thought. For most of history, humans assumed they were at the center of something important. The Earth was the center of the universe. Then the Sun was the center of the solar system, but at least we were in the important solar system. Then the Milky Way was just one galaxy among billions, but at least our galaxy was normal. Now it turns out that even the observable universe, the largest thing we can define with any observational rigor, is probably just a small bubble inside something unimaginably larger. We are not at the center, we are not special, we are not even looking at most of what exists. Some people find that depressing. The universe is too big, too indifferent, too empty. We're specks on a speck, orbiting a speck in a galaxy that's one of trillions, and even those trillions are just the ones close enough for their light to reach us. The rest is out there somewhere, doing its thing, completely unaware that we exist, and completely unobservable to us in return. What's the point of any of it if we're that small? But here's another way to look at it. The fact that we can figure any of this out at all is remarkable. We're a species that spent most of its existence thinking the stars were holes in a shell. A few centuries of looking up with better tools and doing math on the results, and we've mapped the structure of spacetime itself. We've traced the history of the universe back to fractions of a second after it began. We've measured the afterglow of creation. We've calculated distances so large that light takes billions of years to cross them, And we've done it all from the surface of one small planet without ever leaving our own solar system. The edge of the observable universe is not a wall, it's not a place you could travel to and touch. It's a consequence of the fact that information moves at a finite speed and the universe has a finite age. If you could somehow teleport to a galaxy sitting right at our cosmic horizon and looked around, you'd see your own observable universe centered on that new location. A different 93 billion light-year sphere with a different collection of galaxies inside it, some overlapping with ours, some entirely new. The Milky Way, from that vantage point, would be sitting at the edge of their observable universe, just barely visible if they had powerful enough telescopes. And if you traveled farther, you'd keep finding new observable universes, each one a sphere of visibility centered on wherever you happen to be standing. That's the trick. The observable universe isn't a thing, it's a perspective. It's what you can see from where you are, limited by how long light has had to travel and how much space has expanded in the meantime. Every observer in the universe has their own cosmic horizon, their own bubble of observability. Most of those bubbles don't overlap with ours. So when we ask what's beyond the observable universe, we're not asking about some mysterious other realm. We're asking about the rest of the universe, the part that exists but hasn't had time to send us a postcard yet. And based on everything we know about physics, that part is probably a lot like this part. Stars, galaxies, black holes, planets, dust, dark matter, dark energy, all the same ingredients, just rearranged in ways we'll never see, unless the universe isn't like that at all. Unless the universe isn't like that at all. Which brings us to the part that keeps philosophers awake at night and makes physicists start drinking at lunch. What if there really is an edge? Not the edge of what we can see, but an actual boundary where the universe just stops. And on the other side of that boundary, there's nothing. Not empty space, not a vacuum waiting to be filled. Nothing. True nothingness. The kind that makes your brain itch when you try to picture it. Most people think they know what nothing means. You open the fridge, there's nothing to eat. You check your bank account, there's nothing left. You ask someone what they're thinking about and they say nothing. But that's not nothing. That's just the absence of the thing you were looking for. The fridge still has air in it. The bank account still exists as a database entry somewhere. The person saying nothing is still thinking about something, they're just not telling you what it is. True nothingness is different. True nothingness is the absence of everything. Not just matter and energy, not just particles and fields. Space itself, time itself, the laws of physics, the dimensions that give reality its shape, all of it gone. Not hidden, not transformed, not waiting on the other side of some barrier. Just not there. Never was, never will be. Doesn't even have the property of being absent because absence implies a place where something could be, and there's no place. Try to picture it. You can't. Your brain won't let you. Every time you try to imagine nothing, you end up imagining something. A dark room, empty space, a blank canvas. But a dark room still has walls. Empty space still has space. A blank canvas is still a canvas. You're sneaking in a stage for the nothingness to perform on, and that's cheating. True nothingness doesn't have a stage. It doesn't have an inside or an outside. It doesn't have a before or an after. It just isn't. The problem gets worse when you try to apply this to the universe. If the universe has an edge, a real boundary where everything stops, what's on the other side? The obvious answer is nothing. But what does that mean physically? Does space just end? Can space do that? And if space ends, does time end too? Can you have time without space, or space without time? General relativity says no. Space-time is a package deal. You don't get one without the other. So if the universe has a boundary, it's not just a wall in space, it's a boundary of space-time itself. Step across it, and there's no space to step into, and no time for the stepping to happen in. The concept eats itself. Some cosmologists have tried to salvage the idea by proposing that the universe has a boundary, but it's not the kind you can reach by traveling. Imagine the surface of a sphere. You can walk in any direction on the surface forever, and you'll never hit an edge. That's because the surface is finite but unbounded. It curves back on itself. The universe could work the same way. Space could be curved in such a way that if you traveled far enough in one direction, you'd eventually end up back where you started without ever encountering a wall. Finite but no edge. That model works mathematically. Einstein played with versions of it, but it requires the universe to have a specific shape and a specific density of matter and energy distributed throughout it. When astronomers measure the geometry of space using the cosmic microwave background, they find that the universe appears to be flat, at least within the observable portion, not curved like a sphere, flat like an infinite sheet. If that flatness extends beyond what we can see, and most models suggest it does, then the universe is probably infinite. No boundary, no edge, just more universe forever. But flat doesn't necessarily mean infinite. There are other topologies you can construct where space is flat locally but wraps around globally, like a three-dimensional version of a video game where you walk off one side of the screen and reappear on the other. Mathematicians call these structures toroidal or multi-connected spaces. They're possible in principle. The universe could be shaped like a donut or a pretzel or something even stranger, and we wouldn't know unless we looked far enough to see the pattern repeat. So far, we haven't seen any evidence of that. The observable universe looks pretty uniform in all directions with no obvious signs of wrapping or repetition. That doesn't rule out a finite universe, but it pushes the boundary, if there is one, far beyond the reach of our telescopes. Let's assume, for the sake of argument, that there is no boundary. The universe just goes on forever. Does that mean nothing exists? Not quite. It means that the question of what's outside the universe doesn't make sense because there is no outside. The universe is everything. All of space, all of time, all of matter, all of energy. Asking what's beyond it is like asking what's north of the North Pole. The question contains a category error. North is a direction you can travel within the framework of the Earth's surface. Once you reach the pole, the concept stops applying. Similarly, beyond is a spatial concept that only makes sense within the framework of space. If the universe is all the space there is, there's no beyond to talk about. That answer satisfies some people. It irritates others. It feels like a dodge. Sure, mathematically the question might be malformed, but that doesn't stop the brain from wanting to ask it. If the universe is everything, what is everything sitting in? What is the background against which existence happens? And if there's no background, how did existence get started in the first place? Philosophers have been chewing on this for millennia. The ancient Greeks argued about whether the universe was infinite or bounded. Aristotle thought it had to be finite because infinity was a concept the human mind could think about, but nothing physical could embody. Infinite meant incomplete, and the cosmos was supposed to be perfect and whole. Later thinkers disagreed. Giordano Bruno, in the 16th century, proposed that the universe was infinite and filled with countless worlds. The Catholic Church burned him at the stake for that and other heresies, which did not settle the argument, but did make people more cautious about how loudly they discussed it. Modern cosmology hasn't made the question go away, it's just translated it into math. And the math, depending on which assumptions you plug in, can give you an infinite universe, a finite one, or something in between? None of those answers feels complete because they all push the deeper question one step further back. If the universe is infinite, how did an infinite thing begin? If it's finite, what's outside the boundary? If it loops back on itself, why does it loop? Every answer raises another question. Now let's talk about nothing again. Because there's a difference between the nothing that might sit outside a finite universe and the nothing that quantum mechanics says can't actually exist. A vacuum, in the everyday sense, is a region of space with no matter in it. Suck the air out of a jar and you've created a vacuum. But that vacuum isn't truly empty. It still has space. It still has time. It still has quantum fields permeating every point. Those fields, according to quantum mechanics, are never completely still. They fluctuate. Even in the most perfect vacuum you could create, particles and antiparticles are constantly popping into existence for the briefest fractions of a second before annihilating each other and disappearing. The energy for this comes from the uncertainty principle, which says that you can never pin down both the energy of a system and the duration of an event with perfect precision. Borrow a little energy for a short enough time and the universe won't notice. That borrowed energy manifests as virtual particles, a bubbling quantum foam that fills even the emptiest regions of space. This has been tested. The Casimir effect, first predicted in 1948, shows that if you place two metal plates very close together in a vacuum, the plates will experience a tiny attractive force. The reason is that the quantum fluctuations between the plates are restricted by the geometry. Only certain wavelengths can fit in the gap. Outside the plates, all wavelengths are allowed. The imbalance in the number of virtual particles on either side creates a measurable pressure that pushes the plates together. The effect is real. Physicists have measured it, which means the vacuum is not empty, it's busy. So when we talk about true nothingness, we're not talking about a vacuum. We're talking about the absence of the quantum fields themselves, no space for the fields to exist in, no time for the fluctuations to happen across, no framework at all. Can that state exist? Quantum mechanics says probably not. If space and time are emergent properties of quantum fields, and some interpretations suggest they are, then you can't have a region where the fields don't exist, because without the fields there's no region for them not to exist in. The whole concept collapses into a semantic loop. Some physicists take this as evidence that true nothingness is not just hard to imagine, it's physically impossible. The universe, or multiverse, or whatever you want to call the totality of existence, can never be truly empty because the machinery that generates reality is built into the fabric of space-time itself. There is no off switch. Existence, in some form, is the default state. Alan Guth, one of the architects of inflation theory, once said that the universe is the ultimate free lunch. You don't need a cause or a creator or a prior state, because the total energy of the universe, when you account for gravity, might be exactly zero. Matter and radiation have positive energy, gravity has negative energy. Add them up and they cancel. A universe that starts with nothing, in the sense of zero total energy, can inflate into something without violating any conservation laws. It doesn't even cost anything. That idea, which traces back to work by physicists like Alexander Vilenkin in the early 1980s, suggests that universes can emerge spontaneously from quantum fluctuations in a timeless, spaceless void. Not the kind of void where you have empty space sitting around waiting for something to happen, a deeper void. A state with no space-time at all. Just quantum uncertainty doing what quantum uncertainty does, which is refuse to sit still. Fluctuations occur. Some of those fluctuations are large enough to nucleate a bubble of space-time. That bubble inflates. A universe is born. The whole process is probabilistic. It doesn't need a trigger. It just happens because the math says it can. If that's correct, then true nothingness in the absolute sense never exists because even the void has quantum properties. And if the void has quantum properties, it's not nothing, it's something, just something very different from the something we're used to. The boundary between existence and non-existence gets blurry at that level. You end up in a situation where asking whether the universe came from nothing is the wrong question. The universe came from a state that we don't have good words for because our language evolved to describe things with spatial extent and temporal duration, and the pre-universe state had neither, or both, or something orthogonal to both that we can only talk about using equations that make philosophers' heads hurt. But let's say we ignore all of that and go back to the simpler question. If the universe does have a boundary and there is something like an outside, what would that outside be? One possibility is that the outside is another space-time, not empty, just different. The universe we live in could be one bubble in a larger structure, sometimes called the multiverse, though that term gets overloaded with different meanings depending on which physicist you ask. In this version, the space beyond our cosmic horizon isn't nothing. It's more space, but space that isn't causally connected to ours. Different bubbles, different physical constants, different laws, maybe even different numbers of dimensions. Each bubble is its own universe. The collection of all bubbles is the multiverse. The background in which the bubbles float could be something like a higher dimensional space, or it could be a kind of quantum substrate that isn't space or time in the usual sense but can give rise to both under the right conditions. That model gets around the problem of true nothingness by saying there's always something, just not always something that looks like the universe we observe. The multiverse is eternal, or at least it doesn't have a beginning in any conventional sense. Bubbles form, inflate, evolve, maybe collapse. The process runs forever in all directions, generating an infinite variety of universes, most of which are nothing like ours. We happen to live in one of the rare bubbles where the constants and laws are tuned just right for stars and planets and life. Not because anyone tuned them, but because in an infinite multiverse, every possible configuration happens somewhere. We're in this one because this is the kind of bubble where observers like us can exist. It's selection bias on a cosmic scale. The philosophical implications of that are uncomfortable. If every possible universe exists somewhere in the multiverse, then the fact that we're in this particular universe tells us nothing about why the universe is the way it is. The constants of nature aren't special, they're just the random draw we happened to get. Some bubbles have stronger gravity, some have weaker electromagnetism, some don't have atoms, some don't have time. Most of them are sterile, empty, or so chaotic that nothing interesting ever happens. We don't see those, we see this one. Not because it's privileged, just because it's the one we're in. That reasoning bothers people who think the universe should be explicable from first principles. If you can't predict the constants because they're different in every bubble, then you've given up on explaining them. You've traded a physics problem for an anthropic shrug. Some scientists hate that trade, others think it's the most honest answer we're going to get. Either way, this version of Beyond the Universe still isn't true nothingness. It's an infinite mosaic of spacetimes embedded in some kind of higher structure. The structure might be strange, it might not have time in the way we understand time. But it's not the absence of everything. It's the presence of something we don't have the tools to observe directly. So we circle back. If there is a place, or a state, or a concept that really is nothing, no space, no time, no fields, no dimensions, no laws, no structure, no anything, can that state exist? And if it did exist, could anything come from it? The answer from physics is that we don't know, And we might never know because the tools we use to investigate reality all assume that reality is there to investigate. You can't probe nothingness with a telescope or a particle accelerator. You can't write down an equation describing it because equations are structures and structures are something. Even the act of thinking about nothingness turns it into an object in your mind, which makes it not nothing anymore. Some philosophers argue that true nothingness is logically impossible. If nothing existed, there would be no laws of logic, no rules constraining what can or can't happen. In that environment, anything could happen, including the spontaneous appearance of something. So nothingness is unstable. It can't last. The moment you have nothing, you get something, because there's no law preventing it. That's not a scientific argument. It's a metaphysical one, but it's surprisingly hard to refute. Other philosophers take the opposite view. They say that nothingness is the natural state and existence is what needs explaining. Why is there something rather than nothing? That's one of the oldest questions in philosophy, and after thousands of years, nobody has an answer that satisfies everyone. Theists say God created everything, but that just moves the question. Why is there God rather than nothing? Physicists say the universe emerged from a quantum fluctuation, but quantum fluctuations require a framework of quantum mechanics. Why is there quantum mechanics rather than nothing? You can keep pushing the question back forever. At some point, you hit bedrock, and the bedrock is either nothing or something, and neither option makes sense. The terrifying part, if you want to call it that, is that this isn't just a thought experiment. If the universe really does have a boundary, and if the region beyond that boundary is truly nothing, then we are surrounded by it. Not in a spatial sense. There's no direction you can point to and say, that way lies the void. But conceptually, everything that exists is floating in or on or against a background of absolute non-existence. Existence is an island. Step off the island and there's no ocean, no air, no void. There's just the absence of stepping, the absence of you, the absence of the possibility of anything. Some people find that idea freeing. If existence is bounded, then it has a shape, it's comprehensible, it's finite. You can, in principle, catalog it, draw a map, understand it completely. There's comfort in limits. Other people find it suffocating. If existence is all there is, and beyond it is nothing, then we're trapped. Not physically trapped, because there's nowhere to escape to. Conceptually trapped. Existence is a cage, and the walls are made of the absence of everything. You can't break out because breaking out would require a place to break into, and there isn't one. You're here, in the universe, and here is all there is, forever. Most cosmologists don't lose sleep over this. The math suggests the universe is probably infinite anyway, which means there's no boundary and no void, and the whole question is moot. But the math also allows for finite models, and as long as those models are consistent with observation, we can't rule them out. So the question stays open. And every so often, someone writes a paper exploring what a boundary would look like, or whether spacetime could end, or what true nothingness would mean for quantum field theory. The papers are technical and dense, and almost nobody reads them. But they exist because the question won't go away. Here's the part that should keep you up at night. If true nothingness is impossible, if quantum mechanics or logic or metaphysics prevents the existence of a state with no structure at all, then existence is mandatory. There has to be something, always, everywhere, or every when, if time is part of the package. And if existence is mandatory, then the universe or the multiverse or whatever the largest structure is has no beginning and no end. It just is. It always has been and it always will be. Not because something made it that way, but because non-existence is not an option. That makes reality feel less like a thing that happened and more like a thing that simply is, an eternal, necessary structure. You don't get to ask why it exists, because existence is not contingent on anything. It's the default, the baseline, the state from which everything else follows. And if that's true, then the multiverse is almost certainly real. And if that's true, then the multiverse is almost certainly real. Not real in the sense that we've seen it or photographed it or sent a probe through the membrane separating our bubble from the next one over. Real in the sense that the math that describes our universe keeps spitting out solutions that include other universes whether we want them or not. Real in the sense that multiple independent lines of theoretical reasoning all converge on the same uncomfortable conclusion. We are not alone, not in the sense of aliens, though statistically those probably exist too, alone in the sense of being the only universe. That idea, the one humans clung to for most of history, the notion that this cosmos with its particular laws and constants and dimensions is the only game in town, is looking less and less tenable every year. The multiverse is not one idea. It's a family of ideas, each with its own origin story and its own implications. Some versions are conservative, barely extending beyond what we can observe. Others are so extravagant that they make infinity look modest. And the strangest part is that none of these ideas were invented because physicists wanted them. They emerged as side effects of trying to solve other problems, unavoidable consequences of equations that worked too well to ignore. Let's start with the version that has the most momentum right now among cosmologists, the one that falls out of inflation theory almost automatically. It's called the inflationary multiverse, and it begins with a question that inflation was designed to answer but ended up making worse. In the early 1980s, Alan Guth proposed that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. This solved several puzzles. It explained why the universe looks so uniform in all directions, even though distant regions never had time to interact and smooth themselves out. It explained why space appears flat instead of curved. It explained why we don't see magnetic monopoles and other exotic relics that earlier models predicted should be everywhere. Inflation was elegant. It worked. Physicists loved it. Then Andrei Linde, working independently in the Soviet Union, developed a variation he called chaotic inflation. In Linde's model, inflation doesn't happen once and stop. It happens continuously in different regions of space at different times. Picture a pot of boiling water. Bubbles form, expand, break the surface. While one bubble is finishing, others are just starting. Linde's version of inflation behaves the same way. The inflating field that drives expansion never shuts off completely. It keeps creating new bubbles of space. Each bubble exits inflation and becomes a universe. Our universe is one bubble. The bubbles next to us are other universes. The process runs forever, generating an infinite number of separate regions, each with its own Big Bang, each isolated from the others by the still inflating space between them. This wasn't speculation. This was a direct consequence of taking inflation seriously and following the math. If the field driving inflation is subject to quantum fluctuations, and it almost certainly is because everything at that scale is subject to quantum fluctuations, then some regions will stop inflating while others keep going. The regions that stop become universes. The regions that keep going produce more bubbles, which stop and become more universes, and the cycle never ends. Inflation, once it starts, is eternal. Not because anyone decided it should be, because the physics doesn't give you a choice. Linde described it plainly. Different regions exit inflation at different times, each producing a separate Big Bang, a separate universe. The process has no off switch. Once inflation begins anywhere, it runs forever, spawning an infinite tree of bubble universes branching off from one another in a space that is itself constantly expanding faster than light. The space between bubbles grows so quickly that the bubbles can never touch. They're causally disconnected. Light from one bubble will never reach another. You could be standing on the edge of our bubble, if edges meant anything in this context, and you would have no way of knowing that another universe was right next to you because the inflating space in between is pulling you apart faster than any signal can cross. That's the inflationary multiverse. It's not a fringe idea. It's mainstream enough that cosmologists argue about its details at conferences without getting laughed out of the room. Most physicists who accept inflation, and that's most physicists, accept that eternal inflation is a natural consequence of the same mechanism, which means they accept, at least provisionally, that we live in a multiverse whether we like it or not. Now let's add string theory to the mix, because that's where things get truly out of hand. String theory, which is really a family of related theories rather than one unified framework, attempts to describe all particles and forces as different vibrational modes of tiny one-dimensional strings. The math is beautiful. The problem is that the math has a ridiculous number of solutions. Early estimates suggested thousands, then millions, then someone sat down and calculated more carefully and came back with a number that made everyone uncomfortable. 10 to the power of 500. That's not a typo. 10 to the 500, a 1 followed by 500 zeros. Each solution corresponds to a different configuration of how the extra dimensions required by string theory are curled up and hidden. And each configuration gives you a different set of physical laws, different masses for particles, different strengths for forces, different values for constants like the speed of light or the charge of an electron. Each one is a different universe. Physicists call this the string landscape. Imagine a vast terrain with 10 to the 500 valleys. Each valley is a possible universe. Our universe sits in one of those valleys. The other 10 to the 500 minus 1 valleys are other universes with different rules. Most of them are boring. No stars, no atoms, no complexity. The constants are tuned wrong, and nothing interesting ever happens. A few of them, maybe a vanishingly small fraction, have the right combination of parameters to allow stars and chemistry and life. We're in one of those. Not because we're special, because observers can only exist in the tiny subset of universes where the laws permit observers. This is where the anthropic principle comes in, and where a lot of physicists start to get uncomfortable. The anthropic principle says that the properties of the universe we observe must be compatible with the existence of observers, because if they weren't, we wouldn't be here to observe them. That sounds like a tautology. It is a tautology. But it's also a selection effect, and selection effects are real. Here's an example. Imagine you're standing on a beach. You notice that the sand near the water is wet. You could ask, why is the sand wet here? And you could come up with a complicated physical explanation involving waves and tides and the porosity of sand grains. Or you could just note that you're standing near the water, and sand near water is always wet. The fact that you're standing in a place where the sand is wet tells you nothing about sand in general. It just tells you that you're near the water. If you were standing inland, the sand would be dry. You're at the beach, so it's wet. That's selection bias. You're sampling a non-representative part of the environment, because that's the part of the environment where you happen to be. The multiverse version of this argument says that we live in a universe where the constants are tuned for life, not because the constants are special, but because we can only live in a universe where the constants are tuned for life. The other universes are still out there. We don't see them because we're not in them. We're in this one. The one where carbon is stable and stars burn long enough to cook heavy elements and planets form and chemistry gets complicated enough to produce molecules that replicate. That universe is rare in the landscape, but the landscape is so big that rare doesn't matter. Rare times 10 to the 500 is still a lot. Some scientists love this reasoning. It explains why the constants appear fine-tuned without requiring a fine-tuner. We're not the product of design, we're the product of statistics. Roll the dice 10 to the 500 times and eventually you get a universe that looks like ours. Other scientists hate it. They argue that the anthropic principle is a surrender. If you can't predict the constants because they're different in every universe, then you've given up on doing physics. You've replaced explanation with observation. You're just cataloging what is instead of deriving why it has to be that way. And worse, you've made the theory untestable. If every possible set of laws exists somewhere in the multiverse, then the theory predicts everything and therefore predicts nothing. It's not falsifiable. And if it's not falsifiable, is it even science? That debate has been running for decades and shows no sign of resolving. Meanwhile, the math keeps producing multiverses. There's another type of multiverse that doesn't require inflation or string theory. It comes from quantum mechanics, and it's arguably the strangest of the bunch. In 1957, a graduate student named Hugh Everett was working on his PhD thesis at Princeton. He was trying to solve a problem that had been bothering physicists since the early days of quantum mechanics. When you measure a quantum system, the system seems to collapse from a state of multiple possibilities into one definite outcome. Before you measure, the electron is in a superposition of spin up and spin down. After you measure, it's one or the other. The question was, what causes the collapse? How does the universe decide which outcome to pick? The standard interpretation, formulated by Niels Bohr and others in the 1920s, said that measurement itself causes the collapse. The act of observation forces the quantum system to choose, but that raised more questions than it answered. What counts as a measurement? Does it require a conscious observer? If so, does that mean the universe didn't have definite properties before life evolved? The whole thing felt ad hoc and unsatisfying. Everett proposed a radical alternative. He said, there's no collapse. The quantum system doesn't choose one outcome. It realizes all of them. When you measure the electron, the universe splits into two branches. In one branch, the electron is spin up. In the other branch, it's spin down. Both outcomes happen. Both versions of you see a result. You just can't see the other version because the branches are decohered, meaning they no longer interact. From your perspective, it looks like the universe picked one outcome. From a God's eye view, it realized both. This is the many worlds interpretation. Every quantum event that has multiple possible outcomes produces a branching. The universe splits into parallel versions of itself, one for each outcome. And since quantum events are happening constantly, everywhere, at every scale, the universe is splitting all the time, trillions of times per second, an unimaginable tree of branching realities, each one as real as the one you're experiencing right now. The many worlds interpretation solves the measurement problem by denying that there is a measurement problem. There's no collapse, there's just branching. The math of quantum mechanics, taken at face value without the collapse postulate, describes a multiverse. Everett didn't add anything to the theory, he just removed the part that said one outcome gets picked and the others disappear. What's left is a multiverse of staggering scope. Most physicists don't believe in many worlds. Or rather, most physicists don't commit to believing in it because the idea makes them deeply uncomfortable. It works mathematically, it's consistent, it makes all the same predictions as the standard interpretation for any experiment you could actually perform. but it multiplies entities beyond necessity. It says that every time you flip a coin, the universe splits into one branch where it's heads and one where it's tails. Both branches are real. Both versions of you continue on, unaware of the other. The number of branches grows exponentially with every quantum event. After a few seconds, there are more branches than there are atoms in the observable universe. After a few minutes, the number is incomprehensibly large. And yet the math doesn't care. The equations work. The predictions match observation. The only thing many worlds requires you to accept is that the universe is vastly larger and stranger than it appears, which, given everything else we've learned about cosmology, shouldn't be that hard to swallow. There are other multiverse models. Some propose that universes exist on separate branes, short for membranes, floating in a higher dimensional space. Collisions between branes could trigger big bangs. Our universe could be one brane in a stack of many, each with its own physical laws, separated by dimensions we can't access. That idea comes from string theory and related frameworks that require more than the three spatial dimensions we experience. The extra dimensions are compactified, curled up so small we can't perceive them. But they're there, and depending on how they're shaped, they could host other universes. Another model, proposed by Lee Smolin in the 1990s, suggests that new universes are born inside black holes. When a black hole forms, it creates a region of spacetime so warped that the interior becomes disconnected from the outside. Smolin speculated that the conditions inside could trigger a new Big Bang, spawning a baby universe that inflates in its own separate spacetime. The baby universe inherits properties from the parent, but with slight variations, like genetic mutations. Over time, this process leads to a kind of cosmological natural selection. Universes that produce lots of black holes have more offspring. The constants and laws that favor black hole formation get passed down. We live in a universe tuned for black holes, which happens to also allow stars and planets and life. Not by design, just by descent. That model is even more speculative than the others. It makes some testable predictions, but so far the observations haven't been precise enough to confirm or rule it out. Still, it's on the table. It's mathematically coherent. It doesn't require any new physics beyond what we already know about general relativity and black holes. And it produces a multiverse as a side effect. Roger Penrose, the Nobel laureate who helped prove that black holes are inevitable in general relativity, has his own multiverse model. He calls it conformal cyclic cosmology. The idea is that the universe goes through cycles. Each cycle begins with a Big Bang and ends in a state where all matter has decayed and only radiation is left. In that far future, the universe has no clocks, no rulers, no way to measure time or distance, because there's no matter left to do the measuring. At that point, Penrose argues, the end of one cycle becomes indistinguishable from the beginning of the next. The infinitely expanded, cold, empty universe at the end of time is mathematically equivalent to the hot, dense state of the Big Bang. So the universe reboots, a new cycle begins, and this has been happening forever. Each cycle is a universe. The sequence of cycles is a multiverse stretched across time rather than space. Penrose claims to have found evidence for this in the cosmic microwave background. Circular patterns that he interprets as the imprints of massive black hole collisions from the previous cycle. Most cosmologists are skeptical. The patterns Penrose points to could be statistical flukes or artifacts of the analysis method. But the idea is out there, published in peer-reviewed journals, defended by one of the most respected physicists alive. It's not fringe, it's just unproven. So here's where we are. Multiple independent frameworks, developed to solve completely different problems, all predict or allow for the existence of a multiverse. Inflation predicts it, string theory predicts it, quantum mechanics, if you take the math seriously, predicts it. Models of black holes and brains and cyclic cosmology all point in the same direction. We are not living in the only universe. We are living in one universe among an enormous, possibly infinite collection. And the kicker is that we can't see any of the others. Not with telescopes, not with particle accelerators, not with any technology we can currently imagine. The other universes, if they exist, are hidden behind horizons we cannot cross. They're in regions of space expanding away from us faster than light. They're on other branches of the quantum wave function that have decohered from ours. They're on other brains in higher dimensions we don't have access to. They're inside black holes. They're in the next cycle, trillions of years in the future, after everything we know has decayed into radiation. They are, by definition, beyond the reach of observation, which brings us back to the testability problem. If you can't observe something, can you claim it exists? Science is supposed to be about evidence. You form a hypothesis, you test it, you see if the predictions match reality. The multiverse doesn't work that way. The hypothesis predicts that there are other universes. The same hypothesis predicts that we can't observe them. How do you test that? Some physicists argue that you don't test the multiverse directly. You test the theories that produce the multiverse as a side effect. If inflation is correct, and we can test aspects of inflation by looking at the cosmic microwave background, then we have to accept eternal inflation and the multiverse it produces. If string theory is correct, and we might be able to test aspects of string theory by finding certain signatures in particle collisions or gravitational wave data, then we have to accept the string landscape and the 10 to the 500 universes it implies. The multiverse isn't the hypothesis. It's a consequence of hypotheses we can test. Other physicists aren't convinced. They argue that accepting untestable consequences is a dangerous road. Once you allow one untestable claim, where do you stop? If the multiverse gets a pass because it falls out of a theory we like, then what about other untestable ideas? You've opened a door that's hard to close. The argument is still running. Papers are published on both sides. Conferences are held. No consensus has emerged. And while the philosophers and physicists argue, the equations keep doing their thing, indifferent to whether anyone believes the results. Here's what the multiverse does that nothing else does. It explains fine-tuning without requiring a tuner. The constants of nature appear to be set with absurd precision. Change the strength of gravity by 1 part in 10 to the 60, and stars don't form. Change the mass of the electron by a few percent, and chemistry breaks. Change the cosmological constant, the energy density of empty space, by almost any amount, and the universe either collapses immediately or expands so fast that matter never clumps into galaxies. The list goes on. The universe looks designed, not metaphorically. It looks like someone went through a list of parameters and adjusted each one to allow for complexity and life. For most of history, that appearance of design was taken as evidence of a designer. The universe is fine-tuned, therefore someone fine-tuned it. The multiverse offers an alternative. The universe isn't fine-tuned. This universe happens to have the right constants, and we're here to notice because we can only exist in a universe with the right constants. The other 10 to the 500 universes have random constants. Most of them are sterile. We don't see those, we see this one. The fine-tuning is an observation selection effect. It's not evidence of design, it's evidence of a large sample size. You can argue about whether that's a satisfying explanation. It doesn't feel as clean as deriving the constants from first principles. But deriving the constants from first principles has been a goal of physics for a century, and nobody has managed it. Every time someone thinks they've found a deeper layer, That layer turns out to have its own free parameters. Maybe there is no deeper layer. Maybe the constants are what they are, because in a multiverse, every possible set of constants gets realized somewhere. We're in a universe with this set. End of story. That explanation bothers people who think the universe should be unique. It bothers people who want physics to predict everything from a single elegant equation. It bothers people who find the idea of 10 to the 500 unseen universes philosophically extravagant, but it doesn't bother the math. The math is fine with it. And if the multiverse is real, then the observable universe isn't just smaller than the whole universe. It's smaller than one universe in a set so large that even calling it infinite might be underselling it. Every possible configuration of matter, energy, space, and time exists somewhere. Every possible history plays out. Every decision you didn't make, you made in another branch. Every random quantum event that could have gone differently did go differently in another universe. The totality of existence is not a cosmos, it's a multiverse. An infinite tapestry of realities layered on top of one another, next to one another, branching off from one another, completely isolated from one another. You are in one thread of that tapestry, this universe, this timeline, this branch of the quantum wave function. You can't see the others. You can't visit them. You can't signal them. But if the math is right, they're there, and they're just as real as you are, which raises a different kind of question. If reality is layered, if there are structures beyond the universe we can see, then maybe space and time themselves aren't fundamental. Maybe they're emergent. Maybe the universe as we know it is just one slice of a higher dimensional object, one projection of something stranger and larger that we don't have the tools to perceive directly. And that thought, more than anything else, is what pushes us past the multiverse into something even harder to wrap your head around. Maybe space and time themselves aren't fundamental. Maybe they're emergent. Maybe the universe as we know it is just one slice of a higher dimensional object, one projection of something stranger and larger that we don't have the tools to perceive directly. That thought is the doorway to the weirdest idea in modern physics, and it's not speculation in the way science fiction is speculation. This is speculation that comes with equations, with peer-reviewed papers, with decades of work by some of the smartest people alive. The idea is that the universe has more dimensions than we can see, not more space in the directions we already know about. More directions entirely. Directions that are perpendicular to up and down, left and right, forward and backward, and also perpendicular to time. Directions that our brains are not wired to visualize because nothing in our evolutionary history prepared us to think about them. And yet the math says they're there, hidden, curled up, or maybe not hidden at all. Maybe we're just looking at them wrong. Let's start with the dimensions you can see. 3 spatial dimensions. You can move forward and backward along one axis, left and right along a second axis, up and down along a third axis. Every point in space can be described by 3 numbers. Your position in a room is a set of coordinates. How far from the wall, how far from the door, how far from the floor. 3 numbers, 3 dimensions. Then there's time. Time is different from space in some obvious ways. You can move in any direction through space. You can only move forward through time. Or at least that's how it feels from the inside. Einstein showed that space and time are not separate things. They're woven together into a single structure called spacetime. Events don't happen at a location. They happen at a location and a time. Spacetime is 4-dimensional. 3 spatial dimensions plus 1 time dimension. That's the universe you experience every day. For most of history, that was enough. 4 dimensions seemed to cover everything. Then, in the early 20th century, a mathematician named Theodore Kaluza was playing around with Einstein's equations of general relativity. He tried extending the equations into 5 dimensions just to see what would happen. 4 dimensions of spacetime, plus 1 extra spatial dimension that nobody had ever seen. When he worked through the math, something strange popped out. The 5-dimensional equations, when you looked at them from a 4-dimensional perspective, split into 2 pieces. One piece was Einstein's gravity. The other piece was Maxwell's electromagnetism. Kaluza had found a way to unify 2 of the fundamental forces of nature by adding an extra dimension. Gravity and electromagnetism weren't separate. They were 2 aspects of the same geometry in 5-dimensional spacetime. The extra dimension was doing the work. It was connecting forces that looked unrelated in 4 dimensions. Oskar Klein, a Swedish physicist, picked up the idea a few years later and asked the obvious question, if there's a 5th dimension, where is it? Why don't we see it? His answer was that the dimension is compactified, curled up into a tiny loop so small that we can't perceive it. Imagine a garden hose. From far away, it looks like a one-dimensional line. You can move along the hose or you can stay put, one dimension. But if you zoom in, you see that the surface of the hose is actually 2-dimensional. There's the length of the hose, and there's the circular direction around the hose. An ant walking on the hose can move forward along the length, or it can walk in a circle around the circumference. 2 dimensions, one large, one curled up. Klein proposed that space has an extra dimension like that. At every point in the 3 spatial dimensions we see, there's a tiny circle curled up perpendicular to all 3. The circle is so small, maybe around the Planck length, which is 10 to the minus 35 meters, that we can't see it. We experience 3 large dimensions and we miss the 4th, because it's wrapped up into a loop smaller than anything we can measure. That was the Kaluza-Klein theory. For a while, people thought it might be the key to unifying physics. Then quantum mechanics came along and made everything more complicated. The theory didn't quite work once you added quantum effects. The predictions didn't match experiment. The idea faded, but it didn't die. It got absorbed into something bigger. String theory emerged in the late 1960s and 1970s as an attempt to describe the strong nuclear force, the force that holds quarks together inside protons and neutrons. Early on, physicists realized that the math worked better if you stopped thinking of particles as points and started thinking of them as tiny loops of energy. Strings. The strings vibrate, and different vibrational modes correspond to different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. All the particles in the Standard Model are just different notes played on the same fundamental string. The problem was that the equations only worked in a specific number of dimensions, not 4, not 5. Either 10 or 26, depending on which version of string theory you were using. The version that included fermions, the particles that make up matter, required 10 dimensions, 9 spatial dimensions plus time. That's 6 more spatial dimensions than we see. At first, this seemed like a deal breaker. The universe clearly has 3 spatial dimensions. Any theory that required 10 was obviously wrong. Then someone remembered Kaluza and Klein. What if the extra dimensions are compactified? What if they're curled up so small that we don't notice them? The idea was revived. String theory needed extra dimensions. Kaluza-Klein theory showed how to hide them. Combine the two and you get a framework where the universe has 10 dimensions, but 6 of them are compactified into a tiny shape, and the remaining 4 are the large spacetime we experience. The shape of the compactified dimensions matters a lot. The way the extra dimensions are curled up determines what kinds of particles and forces appear in the 4-dimensional world. Different shapes give you different physics. And there are a lot of possible shapes. Mathematicians call them Calabi-Yau manifolds, and they're extraordinarily complicated. Picture a six-dimensional object that's smooth and curved in very specific ways to satisfy certain equations. You can't picture it. Nobody can. The human brain doesn't do six-dimensional visualization, but the math describes them precisely. In the early 2000s, string theorists started counting how many different Calabi-Yau shapes were possible. The number kept growing, thousands, then millions. Then someone did a more careful estimate and came back with 10 to the power of 500. Each shape corresponds to a different vacuum state of string theory, a different possible universe with different laws of physics. That's the string landscape we talked about earlier. Each point in the landscape is a different way to curl up the extra dimensions, and each gives you a different four-dimensional universe. So here's where we are. String theory, which is the leading candidate for a theory of everything, a framework that could in principle unify all the forces and particles into one coherent structure, requires extra dimensions. At least 6. Those dimensions are hidden from us because they're compactified, and the way they're compactified determines what the universe looks like at the scales we can observe. The four-dimensional universe we experience is just a shadow cast by a 10-dimensional structure we can't see. That's not the end of it. In the mid-1990s, string theorists discovered something called duality. Different versions of string theory, which had been developed independently and looked completely different, turned out to be related. They were different ways of describing the same underlying structure. If you took one version and changed certain parameters, you could transform it into another version. The 5 major string theories weren't 5 theories, they were 5 corners of one larger framework. That framework is called M-theory. The M stands for different things depending on who you ask: membrane, mother, mystery, magic. Edward Witten, one of the architects of M-theory, has never committed to a single interpretation. What matters is that M-theory unifies the string theories, and it does so by adding another dimension. M-theory requires 11 dimensions, 10 spatial dimensions plus time. The 11th dimension changes the picture. In 10-dimensional string theory, the fundamental objects are one-dimensional strings. In 11-dimensional M-theory, the fundamental objects include two-dimensional membranes, or brains for short. Our universe could be a three-dimensional brain, a three-dimensional surface embedded in a higher dimensional space. Everything we see, every particle, every force, every star and galaxy could be confined to this brain. We can't leave it, we can't see off it. We're stuck on a three-dimensional sheet floating in an 11-dimensional bulk. That's the brain world scenario. It sounds like science fiction. It's not. It's a direct consequence of taking M-theory seriously, and M-theory is not fringe physics. It's the most developed framework we have for trying to unify general relativity and quantum mechanics. The equations work, the dualities are real, the predictions, where we can test them, match what we see. The theory requires 11 dimensions. If the theory is right, those dimensions exist. Now let's talk about what hidden really means in this context. When physicists say the extra dimensions are compactified, they don't mean hidden in the sense that they're behind a curtain you could pull back. They mean the dimensions are curled up at every point in space. Right now, as you're sitting there, there are 6 or 7 extra dimensions curled up into a tiny shape smaller than an atom, smaller than a nucleus, smaller than a quark. The shape is there at every point in the room, but it's so small that nothing you do can probe it. You move through 3 large dimensions. You also move through the compactified dimensions, but the motion is so constrained by the geometry of the curl that you don't notice. It's like walking on a surface so smooth that you can't feel the texture. Why can't we see them? Because seeing requires interacting, and interactions depend on energy. To probe smaller distances, you need higher energies. That's why particle accelerators are so big. Smashing particles together at high energy lets you see finer details of their structure. The Large Hadron Collider, the most powerful accelerator we've ever built, can probe distances down to about 10 to the minus 19 meters. That's small. That's a tenth the size of a proton. But it's nowhere near the Planck length, which is 10 to the minus 35 meters. The compactified dimensions, if they exist, are curled up at scales 16 orders of magnitude smaller than what the LHC can reach. We're not even close. We'd need an accelerator the size of a galaxy to probe those distances directly. We don't have that. We're not getting it anytime soon. So how do we know the extra dimensions are there if we can't see them? We don't, not directly. What we can do is look for indirect effects. If the extra dimensions exist, they should influence the physics we observe at lower energies in subtle ways. Certain particles might behave slightly differently than expected. Certain forces might have small corrections that show up in precise measurements. Gravitational waves might carry faint signals of the extra dimensions. None of those effects have been detected yet. That doesn't mean the dimensions aren't there. It means either they're too small to produce detectable effects, or we haven't looked carefully enough, or the theory is wrong. There's another possibility that's been explored more seriously in the last 20 years. What if the extra dimensions aren't compactified? What if some of them are large? That idea sounds insane at first. If there's a large extra dimension, why don't we fall into it? The answer is that we might already be inside it, and we just can't move through it because the particles and forces we're made of are confined to a brain. Imagine you're a two-dimensional creature living on the surface of a piece of paper. The paper is your universe. You can move left and right, forward and backward, but not up and down off the paper. Now imagine that paper is floating in a three-dimensional room. The room is a large extra dimension. You can't see it, you can't move into it, but it's there. And certain things like gravity might be able to leak off the paper into the room. Gravity is special. In string theory and brain world models, gravity is not confined to the brain. It propagates through the bulk. All the other forces, electromagnetism, the strong and weak nuclear forces, are stuck on the brain with us. But gravity can spread out into the extra dimensions. That would explain something that has puzzled physicists for a long time. Gravity is absurdly weak compared to the other forces. The electromagnetic force between two electrons is 10 to the 43 times stronger than the gravitational force between them. Why is gravity so weak? One possibility is that it's not actually weak, it's just diluted. Gravity spreads through extra dimensions, so by the time it gets back to our brain, it's been diluted by the extra volume. The other forces don't have that problem because they're confined to the brain. They're concentrated. Gravity is not. If that's true, then gravity should start behaving differently at very short distances, distances where the extra dimensions start to matter. Several experiments have looked for this. They measure the strength of gravity between objects at smaller and smaller separations to see if there's a deviation from Newton's inverse square law. So far, the measurements are consistent with Newton down to distances of about 10 micrometers, 1/100th of a millimeter. If the extra dimensions are larger than that, we should have seen something by now. We haven't. That doesn't rule out large extra dimensions. It just sets a limit. If they exist, they're smaller than 10 micrometers. That's still a lot larger than the Planck length. If the extra dimensions are anywhere in that range, between 10 micrometers and 10 to the minus 35 meters, they could in principle be detected by experiments we might be able to build. Not today, not with current technology. But maybe in the next generation of colliders or gravitational wave detectors. There's a window. a narrow one, but real. The brain world picture opens up even stranger possibilities. If our universe is a brain floating in a higher dimensional bulk, there could be other brains nearby. Other universes, separated from ours not by vast distances in the 3 dimensions we see, but by a tiny gap in an extra dimension we can't access. Parallel universes, literally parallel in the geometric sense, sitting a fraction of a millimeter away in a direction we don't have a word for. Those other brains would be invisible to us because light is confined to our brain. Photons can't jump the gap, but gravity can. If another brain is close enough in the extra dimensions, its gravity might influence our brain in ways we could detect. Some cosmologists have speculated that dark matter, the mysterious stuff that makes up most of the matter in the universe and doesn't interact with light, could be ordinary matter living on another brain. We can't see it because it's on a different brain. We can feel its gravity because gravity reaches across the bulk. That's a wild idea. There's no strong evidence for it, but it's not ruled out. Here's the part that bends your brain. If our 3-dimensional universe is a brain embedded in a higher dimensional bulk, then everything you think of as space, every direction you can point, every distance you can measure, is confined to the brain. The bulk is not more space in the directions you know. It's space in directions that are perpendicular to all 3 spatial dimensions simultaneously. You can't visualize that. You can try, you'll fail. The human brain evolved to navigate 3 spatial dimensions. It's very good at that. It's not equipped to visualize 4 or 5 or 10 spatial dimensions. Every attempt to picture it collapses back into 3 dimensions with extra stuff bolted on. That's not what higher dimensions are. They're genuinely new directions, orthogonal to the ones we know, and our brains don't have the hardware to render them. Mathematicians have ways of thinking about higher dimensional spaces without visualizing them. You can describe a 4-dimensional cube, a hypercube, using equations. You can calculate its volume, its surface area, how many edges and vertices it has. You can even project it into 3 dimensions and draw a picture of what the projection looks like. The projection isn't the object. It's a shadow, a flattened representation that captures some of the structure but loses most of it. That's the best we can do. We work with the math, and we trust that the math describes something real even if we can't see it. There's a related idea called the holographic principle that takes this even further. The holographic principle says that all the information contained in a volume of space can be encoded on the boundary of that volume. A 3-dimensional region of space is fully described by the 2-dimensional surface surrounding it. The 3-dimensional universe we experience might be a holographic projection of information stored on a 2-dimensional boundary at the edge of the cosmos. In that view, the extra dimensions aren't hidden, they're redundant. The universe is fundamentally lower dimensional than it appears, and the 3 dimensions we see are an illusion generated by the interplay of information on a distant surface. That idea comes from black hole thermodynamics and was developed by physicists like Gerard Hooft and Leonard Susskind in the 1990s. It's closely tied to string theory and quantum gravity. If it's correct, then the universe is even stranger than the brain world picture suggests. Not only are there extra dimensions we can't see, but the dimensions we do see might not be fundamental. Space itself might be emergent, a derived property of something deeper and simpler that lives in fewer dimensions. The evidence for extra dimensions is indirect and tentative. String theory requires them. That's the main argument. If string theory is the correct description of reality at the smallest scales, then extra dimensions exist because the theory doesn't work without them. But string theory has not been confirmed experimentally. It makes predictions, but most of them are at energy scales we can't reach. The theory is extraordinarily successful mathematically. It unifies forces. It includes gravity. It resolves certain infinities that plague other approaches to quantum gravity. But it hasn't made a single prediction that we've been able to test and confirm in a way that rules out alternative theories. That's a problem. Physics is supposed to be grounded in experiment. A theory that can't be tested starts to look like metaphysics. Some physicists are comfortable with that. They argue that we've reached a point where the energies required to test the fundamental theories directly are so high that experiments are impossible with any foreseeable technology. We have to rely on mathematical consistency and indirect evidence. If the theory is beautiful, and it works mathematically, and it explains things that other theories can't, that's enough to take it seriously, even if we can't test it directly. Other physicists are not comfortable with that. They argue that without experimental confirmation, string theory and extra dimensions are speculative ideas, not established science. Interesting, worth pursuing, but not proven. The debate has been running for decades. Meanwhile, the theory has continued to develop. New dualities have been discovered. New connections to other areas of physics and mathematics have been found. The framework has become more robust. It hasn't become more testable. That's the tension. Here's what we know for sure. The universe we observe has 3 large spatial dimensions and 1 time dimension. That's not in dispute. The question is whether there are more dimensions that we can't see. The math of string theory and M theory says yes. The observations so far don't contradict that. They also don't confirm it. The extra dimensions, if they exist, are either compactified so small that we can't probe them, or they're large but we're confined to a brain and can't access them, or they're emergent structures that don't exist in the way we think dimensions should exist. All 3 possibilities are on the table. None of them are proven. All of them are deeply strange. If extra dimensions are real, the implications are staggering. The universe is not what it looks like. The 3-dimensional space we move through is a slice of something much larger. The laws of physics we observe are shadows of higher dimensional laws. The particles and forces that make up matter are vibrations of strings or brains moving through dimensions we can't see. Everything we know about reality is incomplete. Not wrong, just incomplete. A projection. A lower dimensional cross-section of a higher dimensional structure. And here's the kicker. If the brain-world picture is right, and our universe is one brain among many in a higher dimensional bulk, then the multiverse isn't just a collection of separate spacetimes scattered across an inflating void. It's a stack of universes layered on top of each other in dimensions we don't have access to. The universe next door isn't billions of light years away. It's right here, separated from us by a gap in a direction we can't point to. You could be sitting a millimeter away from another entire universe in the 4th spatial dimension, and you would never know. Light can't cross the gap. Matter can't cross the gap. Only gravity, leaking through the bulk, could carry a signal. And even that signal would be so faint and so distorted that we might never recognize it, unless we already have, because there are anomalies in the data, small ones, things that don't quite fit the standard model, discrepancies in the behavior of certain particles, unexpected patterns in the cosmic microwave background, hints that gravity might be doing something strange at certain scales. None of these anomalies are strong enough to confirm extra dimensions, but they're there, and every time a new experiment runs, every time a new telescope goes online, physicists look at the data and ask the same question. Is this the signal? Is this the first direct evidence that the universe has more dimensions than we thought? So far, the answer has been no, or not yet. The anomalies don't go away, but they don't get strong enough to call a discovery either. The extra dimensions, if they're there, are staying hidden. Maybe they're too small. Maybe we're not looking in the right place. Maybe the theory is wrong and there are no extra dimensions at all. Or maybe the dimensions are there and we're surrounded by a reality we can't perceive, a layered structure of universes stacked in directions we don't have names for, and we're sitting on one thin slice of it, completely unaware that the rest exists. That would make the observable universe look even smaller than it already does, not just a bubble inside a larger cosmos. Not just one universe among trillions in an inflationary multiverse, one three-dimensional slice of an 11-dimensional object we can't see. And if we're that blind to the structure of space itself, what else are we missing? What other forces, what other phenomena are happening just outside the narrow band of reality we have access to? The cosmic microwave background might be glowing with signals from the bulk that we don't know how to read. Gravity might be pulling on us from directions that don't exist in our three-dimensional framework. Dark matter might not be matter at all. It might be the gravitational shadow of objects living in a higher dimension, objects we can never see because they're not on our brain. We call it dark because it doesn't emit light. Maybe it doesn't emit light because it's not here. It's next door, in a place we can't go. And that brings us to another anomaly. One that doesn't fit into any framework cleanly. One that suggests something beyond our cosmic horizon is pulling on us in a way we can't explain. A flow, a tug, a current running through the universe at scales so large that it shouldn't exist. And yet it's there, recorded in the motions of galaxy clusters across a quarter of the sky. The universe isn't just expanding, something is pulling it, something outside what we can see, or something in a direction we haven't learned to look. And that brings us to another anomaly, one that doesn't fit into any framework cleanly. One that suggests something beyond our cosmic horizon is pulling on us in a way we can't explain. A flow, a tug, a current running through the universe at scales so large that it shouldn't exist. And yet it's there, recorded in the motions of galaxy clusters across a quarter of the sky. The universe isn't just expanding. Something is pulling it, something outside what we can see, or something in a direction we haven't learned to look. Before we get to what's pulling, we need to understand what the universe is supposed to be doing when nothing is pulling. Standard cosmology, the model that has guided astronomy for the better part of a century, says the universe is expanding uniformly in all directions. Space itself is stretching, carrying galaxies away from each other. The expansion was initially slowed by gravity pulling everything back together, but about 5 to 6 billion years ago something changed. The expansion started accelerating, gravity lost, something else took over. That something else is called dark energy. Nobody knows what it is. The name is a placeholder, a label stuck on a mystery while physicists try to figure out what's actually happening. Dark energy makes up about 68 to 70% of the universe, depending on which measurement you trust. Some estimates push it higher. When you combine dark energy with dark matter, the stuff that doesn't emit light but does have gravity, you get a universe that's about 95% made of things we can't see and don't understand. The 5% we do understand, the atoms and light and ordinary matter, is the minority. We live in a universe where the visible part is a rounding error. Dark energy is not a force in the traditional sense. It doesn't pull, it pushes. It's a property of space itself, or at least that's the leading model. The more space you have, the more dark energy you have. As the universe expands, more space gets created, which means more dark energy, which pushes the expansion faster, which creates more space, and the cycle accelerates. The universe is speeding up. Galaxies that are far enough away from us are being carried away faster than the speed of light by the expansion of space itself. not because they're moving through space that fast, because the space between us and them is growing so quickly that the distance increases faster than light can cross it. The discovery that the expansion is accelerating came in 1998 from observations of distant supernovae. Two independent teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, found that very distant Type 1a supernovae were dimmer than expected. That meant they were farther away than they should have been if the universe was expanding at a constant rate or slowing down. The only explanation that fit the data was that the expansion was accelerating. Space was being pushed apart by something that wasn't gravity. The discovery won the Nobel Prize in 2011. It also opened a hole in the middle of cosmology that nobody has been able to close. The simplest explanation for dark energy is the cosmological constant. Einstein introduced it in 1917 as a fudge factor to keep his equations from predicting that the universe should be expanding or contracting. He wanted a static universe because that's what everyone thought the universe was at the time. The constant was a term he added to general relativity that represented a kind of inherent energy in empty space, a repulsive force that pushed outward just hard enough to balance gravity's inward pull. Then Edwin Hubble discovered that the universe was expanding, and Einstein called the cosmological constant his biggest blunder. Except it turns out the cosmological constant might not have been a blunder after all. If you interpret it as the energy density of empty space, the vacuum energy predicted by quantum mechanics, then it does exactly what dark energy appears to do. It pushes space apart. The problem is that when you calculate how much vacuum energy quantum mechanics predicts, you get a number that's 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of physics. Nobody knows how to fix it. So we have dark energy, which behaves like a cosmological constant, and we have no idea why the cosmological constant has the value it does, instead of being 10 to the 120 times bigger, which would have ripped the universe apart before stars ever formed. Another possibility is that gravity behaves differently at very large scales than general relativity predicts. Maybe Einstein's equations are incomplete. Maybe there's a correction term that only matters when you're talking about distances of billions of light years. A modification to gravity could produce the same accelerating expansion without requiring dark energy at all. Several modified gravity theories have been proposed. None of them work as well as general relativity in the regimes where we can test them directly. But they're on the table. Because the alternative, accepting that 70% of the universe is made of something we can't identify and don't understand, is uncomfortable enough that physicists are willing to consider reworking one of the most successful theories ever written. The broad picture, the one everyone agrees on, is that the universe is expanding and the expansion is accelerating. What's causing the acceleration is unknown. NASA's official position on dark energy is, we don't know. That's where the field stands. Decades after the discovery, with thousands of papers written and multiple space missions flown, the answer is still we don't know. That's the baseline. Uniform expansion, driven by something we don't understand, pulling the universe apart in all directions at once. On the largest scales, the universe should look the same in every direction, homogeneous and isotropic, no preferred direction, no large-scale currents or flows. Galaxies move away from us because space is expanding. Galaxies near each other might have small random motions, called peculiar velocities, caused by their mutual gravitational attraction, but those motions are local. They don't add up to a coherent large-scale drift in one direction. That's what the theory says. In 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center published a paper claiming they had found exactly that, a coherent large-scale drift, a flow. Hundreds of galaxy clusters, scattered across a huge patch of sky, were all moving in the same direction with velocities of several hundred kilometers per second, not expanding away from us, flowing, streaming, all heading toward the same region of space like water circling a drain. The team called it dark flow, not because it was related to dark matter or dark energy, though the name caused confusion on that front almost immediately. Dark because they didn't know what was causing it. Flow because that's what it looked like, a current. Kashlinsky and his colleagues measured the motion by looking at the cosmic microwave background. The microwave background is the faint glow of radiation left over from when the universe was 380,000 years old. It's almost perfectly uniform in temperature, but not quite. There are tiny fluctuations, hot spots and cold spots, that map the density variations in the early universe. When a galaxy cluster sits between us and the microwave background, the hot gas in the cluster scatters some of the photons from the background. That scattering distorts the temperature map in a specific way called the Sonja-Zeldovich effect. If the cluster is moving relative to the microwave background, the distortion shifts. Photons get blue shifted in the direction the cluster is moving and red shifted in the opposite direction. Measure that shift and you can calculate the cluster's velocity. Kashlinsky's team looked at hundreds of galaxy clusters and found that their velocities didn't cancel out the way they should if the motions were random. They added up. The clusters were moving together, in bulk, toward a region of sky in the direction of the constellations Centaurus and Hydra. The flow extended out to distances of at least 2.5 billion light-years. That's not local. That's a significant fraction of the observable universe. The result was shocking. The standard model of cosmology says that on the largest scales, matter should be distributed smoothly and moving isotropically. The universe should look roughly the same in every direction. A large-scale flow violates that assumption. If hundreds of galaxy clusters are all drifting in the same direction, something is pulling them, and whatever that something is, it has to be massive. Massive enough to tug on structures spanning billions of light-years, massive enough to override the uniform expansion driven by dark energy. That kind of mass should show up in surveys. We should see it. We don't. The most disturbing explanation is that the mass isn't inside the observable universe, it's outside, beyond the cosmic horizon, in a region of space whose light hasn't had time to reach us yet. If there's an enormous structure out there, something vastly larger than anything we've ever observed, its gravity could reach across the boundary and pull on matter inside our observable bubble. We wouldn't see the structure, we'd just feel its tug. Dark flow, in that interpretation, is evidence that the observable universe is not isolated, it's part of something bigger, and that something bigger is pulling us toward it. That explanation is wild. It's also uncomfortable because it implies that the universe beyond our horizon isn't just more of the same, it's structured. It has concentrations of matter large enough to produce bulk flows across billions of light-years. If that's true, then the assumption that the universe is homogeneous on the largest scales is wrong. The observable universe might be sitting in a relatively smooth patch, but beyond the edge, there could be structures so large that they make superclusters look like grains of sand. Walls, voids, filaments, concentrations of mass that our models never predicted because our models only describe what we can see. The claim was controversial from the start. Other teams tried to reproduce the result and got mixed answers. Some studies found hints of a flow, others found nothing. The problem is that measuring the Sonja-Zeldovich effect is hard. The signal is faint, the clusters are far away. Contamination from foreground sources can mimic the signature of motion. Systematic errors can creep in. Different analysis techniques give different answers. By 2010, some groups were saying the flow was real, and others were saying it was a statistical fluke or an artifact of the data processing. Kashlinsky's team kept pushing. They published follow-up studies with larger samples and better data. In 2013, they used observations from the Planck satellite, which had mapped the cosmic microwave background with unprecedented precision, and found that the flow was still there. The clusters were still moving. The direction and the magnitude matched the original result. Other groups remained skeptical. The debate turned into one of those messy situations where the data are ambiguous enough that smart people looking at the same numbers come to opposite conclusions. Here's what makes the dark flow idea hard to kill. Even if you don't trust the specific measurements, the possibility it points to is allowed by the physics. There's nothing in general relativity or cosmology that says the universe has to be uniform beyond the observable horizon. We assume it is because that's the simplest model and it fits the data we can collect. But simplicity is not a law of nature. The universe could be lumpier than we think. It could have structures so large that we only see a smooth patch because we're sitting in one small region. If those structures exist, they would gravitationally influence the matter we can see. Dark flow is the name we've given to that influence. Whether the specific signal Kashlinsky detected is real or not, the concept it represents, a massive external tug from beyond the horizon, is physically plausible. The implications are unsettling. If the observable universe is not dynamically isolated, if something outside our cosmic horizon is pulling on us, then the picture of the universe as a self-contained expanding bubble is incomplete. We are part of a larger structure. That structure is hidden from view, not because it's far away in the usual sense, but because light from it hasn't reached us yet and may never reach us if the expansion keeps accelerating. We're inside a bubble of visibility. Outside that bubble, the universe continues, and whatever is out there is big enough and close enough, in cosmic terms, that its gravity reaches across the boundary and moves us. That adds another layer to the question of what's beyond the observable universe. If the region beyond the horizon is smooth and uniform, then dark flow doesn't exist, and the anomaly, if it's real, must have some other explanation. But if the region beyond the horizon is structured, if there are super concentrations of mass out there, then we're surrounded by an architecture we can't map. The visible universe is a window. We're looking out through it, but the view is limited, and what's outside the frame might be vastly different from what we see inside it. Dark energy itself could be tied into this. Some models suggest that dark energy isn't constant. It could vary in strength from place to place. If the region of space beyond our horizon has a different dark energy density, that could create pressure differences that push and pull on the matter at the boundary. We'd observe that as a bulk flow. The flow wouldn't be caused by mass. It would be caused by variations in the fabric of space itself. That explanation is speculative. It requires dark energy to behave in ways we have no evidence for. But it's on the table because the alternative explanations are just as strange. Another hypothesis is that the dark flow is an imprint from an earlier phase of the universe's history. Before inflation, or during the transition from inflation to normal expansion, the universe might not have been perfectly smooth. There could have been large-scale density fluctuations that got stretched by inflation but didn't entirely disappear. Those primordial inhomogeneities would create a preferred direction, a gradient in the density of matter or energy that extends beyond the observable universe. We'd see the effect as a bulk flow toward the denser region. The flow isn't being caused by a structure forming now. It's an echo of something that happened 13.8 billion years ago, frozen into the expansion pattern of the cosmos. Testing this is almost impossible with current technology. You'd need to map the motions of galaxy clusters across the entire sky with exquisite precision, separating the signal of the flow from all the other sources of noise and systematic error. Then you'd need to compare that map to the predictions of different cosmological models and see which one fits. Several groups are working on this. The data are getting better, the surveys are getting larger, but the answer is not obvious. The signal, if it exists, is sitting right at the edge of what we can measure. It's the kind of problem that could take another decade to resolve, or longer. What's clear is that the standard model of cosmology, the one where the universe is homogeneous and isotropic on the largest scales and the only large-scale motion is the Hubble expansion, is under strain. Multiple independent observations have found anomalies that don't fit. Dark flow is one of them. There are others. The cosmic microwave background has a feature called the cold spot, a region that's colder than it should be if the fluctuations were purely random. The distribution of galaxy clusters at very large scales shows more structure than some models predict. The alignment of quasar polarization vectors across gigaparsec scales suggests that something is breaking the symmetry of space. None of these anomalies are strong enough on their own to overturn the model, but they're piling up, and they're all pointing in the same general direction. Something about the large-scale structure of the universe is not what we thought. If dark flow is real, and if it's caused by something beyond the observable universe, then we are being pulled, right now. Every galaxy, every star, every atom in your body is drifting in a specific direction through space, carried along by a current so vast that it encompasses a quarter of the visible sky. You don't feel it. The Earth doesn't feel it. The solar system and the Milky Way are moving together, so there's no relative motion to detect locally. But on the largest scales, we're part of a flow, a cosmic river. And the river is heading somewhere. Where is it going? We don't know. The direction points toward a region of sky that looks empty in optical light. There's no obvious structure there. No supercluster large enough to explain the flow. Whatever is pulling us is either too far away to see or too diffuse to stand out against the background. Or it's not a thing at all. It's a property of space, a gradient, a slope in the energy density of the vacuum that pushes and pulls on matter over distances so large that we've only just begun to notice. NASA's position on dark energy is we don't know. The position on dark flow is even less certain. Some researchers say the signal is real and it's one of the most important discoveries in cosmology in the past 20 years. Others say it's an artifact and the flow doesn't exist. The truth is probably somewhere in the middle. There's something there, something anomalous, whether it's a bulk flow caused by a massive external structure or a more subtle effect related to how we're measuring motion on cosmic scales is still an open question. The fact that we're asking the question at all is significant. It means the data are forcing us to consider possibilities that weren't on the table a generation ago. The universe might not be as uniform as we thought. The observable universe might not be isolated, and the structures beyond our horizon might be stranger and larger than anything we've ever imagined. That brings us back to the uncomfortable place we keep ending up. The more we learn about the universe, the more it looks like what we can see is a small, possibly unrepresentative sample of a much larger reality. The observable universe is 93 billion light-years across. The actual universe, if it's infinite, is infinitely larger. If it's finite, it's still vastly larger than what we can see. If the multiverse is real, then our universe is one bubble in a collection that might be infinite in a different sense. If extra dimensions exist, then the three-dimensional space we experience is a slice of a higher dimensional structure we can't access. And if dark flow is real, then something beyond our cosmic horizon is pulling on us, influencing the motion of matter inside the bubble we call home. Each layer makes the universe bigger and stranger. Each discovery shrinks the fraction of reality we have access to. And each time we think we've reached the edge of what's out there, another door opens and we realize we were standing in a hallway, not a room. The observable universe isn't the universe. It's a bubble of visibility inside something larger. And whatever that something is, it's tugging on us in ways we can't fully explain. The question is whether that tug is coming from something physical, a concentration of mass or energy beyond the horizon, or from something deeper, a property of space itself that we haven't learned to describe yet. Or maybe the question is something else entirely. Maybe the universe isn't real in the way we think real means. Maybe the flow, the expansion, the galaxies, the stars, the atoms, all of it are patterns in a structure that's not made of matter or energy at all. Maybe the universe is information, and maybe the reason we keep finding anomalies is that we're looking at the output of a system without understanding the code underneath. Because if the universe is a computation, if reality is being calculated rather than existing in some fundamental physical sense, then everything we've been talking about, the horizons, the dimensions, the multiverses, the flows, all of it could be features of the program, not bugs, not mysteries, just the way the system runs. And if that's true, then the biggest question isn't what's beyond the observable universe. The biggest question is who or what is running the program, and why. Or maybe the question is something else entirely. Maybe the universe isn't real in the way we think real means. Maybe the flow, the expansion, the galaxies, the stars, the atoms, all of it, are patterns in a structure that's not made of matter or energy at all. Maybe the universe is information. And maybe the reason we keep finding anomalies is that we're looking at the output of a system without understanding the code underneath. That thought, the one that makes philosophers reach for a drink and physicists quietly change the subject, is the simulation hypothesis. The idea that everything you're experiencing right now, every sight, every sound, every sensation, every thought, is not happening in a physical universe made of atoms and forces. It's happening inside a computer program, a simulation, running on hardware that exists somewhere outside what we call reality. You are code. The chair you're sitting in is code. The planet beneath your feet is code. The observable universe, with its 93 billion light-year diameter and its 2 trillion galaxies, is code. All of it rendered, calculated, executed by something vastly more advanced than anything we've built, running a program so detailed and so consistent that from the inside it's indistinguishable from a real universe. If that's true, and there are people who take the idea seriously, then every question we've been asking is the wrong question. What's beyond the observable universe? More code. What are the extra dimensions, variables in the simulation? What's pulling the galaxy clusters in dark flow? A feature of the algorithm. The universe isn't a thing, it's a process, and we're inside it. The simulation hypothesis isn't new. Philosophers have been playing with the idea for centuries that reality might not be what it seems. Descartes in the 1600s proposed that an evil demon could be deceiving him about the existence of the external world. The only thing he could be certain of was that he was thinking, "I think, therefore I am." Everything else was potentially an illusion. That was an extreme form of skepticism, a thought experiment designed to find the bedrock of knowledge. Descartes eventually argued his way back to believing in an external world, but the seed was planted. Maybe our senses are lying to us. Maybe the world we perceive is a construct. In the 20th century, the idea got a technological upgrade. If the universe could be an illusion, Maybe it's not a demon doing the deceiving, maybe it's a machine. In 1973, Philip K. Dick gave a speech in which he speculated that we might be living in a computer-programmed reality. He wasn't joking. He thought he had experienced a vision that revealed the truth. Most people dismissed him as eccentric or mentally unwell. Science fiction writers picked up the idea and ran with it. The Matrix, released in 1999, popularized the concept for a generation. Humans trapped in a simulated reality while machines harvest their bodies for energy. The movie was fiction, but it tapped into something that had been simmering in philosophy and early computer science for decades. If you can simulate a world convincingly enough, how would anyone inside that simulation know? The person who turned the simulation hypothesis from a science fiction premise into a semi-respectable philosophical argument is Nick Bostrom, a philosopher at Oxford University. In 2002, Bostrom published a paper titled, "Are You Living in a Computer Simulation?" The paper didn't claim we are in a simulation. It claimed that at least one of three statements about advanced civilizations must be true. And depending on which one is true, the odds that we're living in a simulation could be very high. Here's the argument. Assume that it's possible, in principle, to simulate a conscious mind using a computer. Not today, not with current technology, but eventually. If consciousness is a product of physical processes in the brain, and there's no reason to think it isn't, then those processes can be replicated in software given enough computing power. You'd need a lot of computing power. The human brain has roughly 86 billion neurons, each connected to thousands of others. Simulating that in real time would require hardware far beyond anything we have now. But assume it's possible. Assume that a sufficiently advanced civilization could build computers powerful enough to run detailed simulations of entire worlds, complete with billions of conscious beings who believe they're living in a real physical universe. Now assume that such a civilization would want to run those simulations, maybe for entertainment, maybe for research, maybe to study their own history by recreating it in detail, maybe just because they can. If simulating conscious beings is possible and desirable, then an advanced civilization would probably run a lot of simulations, not one or two, thousands, millions, maybe more. Each simulation could contain billions of conscious observers. So if you add up all the conscious beings across all the simulations, the number of simulated minds vastly outnumbers the number of biological minds living in base reality. Here's where the argument gets uncomfortable. If most conscious beings in the universe are simulated, then any given conscious being, including you, is statistically more likely to be simulated than real. You wake up, you look around, you see a world. The question is, are you in the base reality, or are you in one of the countless simulations being run by some advanced civilization? You can't tell from the inside. The simulation is designed to be consistent. It obeys the same rules every time. From your perspective, it feels real. But feelings don't settle the question. If there are 1 trillion simulated people for every real person, the odds are 1 trillion to 1 that you're simulated. That's the core of Bostrom's argument. It's not a claim that we are in a simulation. It's a claim about probabilities. If advanced civilizations can run ancestor simulations, and if they choose to run a lot of them, then most observers are simulated. Therefore, you're probably simulated. Unless one of the assumptions is wrong. Bostrom laid out 3 possibilities, and he argued that at least one of them has to be true. First possibility, almost all civilizations go extinct before they reach the level of technology needed to run realistic simulations. Maybe nuclear war wipes them out. Maybe climate collapse. Maybe artificial intelligence goes rogue and kills everyone. Maybe there's some other bottleneck we haven't encountered yet that reliably destroys civilizations before they get to the post-human stage. If that's true, then there are no advanced civilizations running simulations, which means we're not in one. Second possibility: advanced civilizations reach the capability to run simulations but choose not to. Maybe they lose interest. Maybe they decide it's unethical. Maybe their priorities shift and they spend their resources on something else. If no advanced civilization ever bothers to run large numbers of ancestor simulations, then again, we're not in one. Third possibility: we are almost certainly living in a simulation. If civilizations don't go extinct and they do run simulations, then the number of simulated realities vastly exceeds the number of base realities. By pure statistics, we're in a simulation. That's the trilemma. Pick one. Either civilizations die out or they abstain from running simulations, or we're living in one. Bostrom doesn't say which option is correct. He just points out that the logic forces you to accept at least one of them. And if you think civilizations can survive and you think they'd be interested in running simulations, then the third option starts to look uncomfortably plausible. The argument is clever. It's also maddeningly hard to refute because it doesn't make testable predictions. If we're in a simulation, the simulators could have programmed the universe to behave exactly like a non-simulated universe. Any test you devise to check whether you're in a simulation could itself be part of the simulation. The code could include false results that make the simulation look like base reality. You're trapped. There's no experiment you can run that definitively proves you're not in a simulation, because any evidence you collect is evidence generated by the system you're trying to test. It's like asking a character in a video game to prove they're not in a video game by examining the game world. Everything they find will be consistent with the game because they can't access anything outside it. Some people find this argument liberating. If we're in a simulation, then the universe isn't as big or as old or as fundamental as we thought. It's a construct, a program. And programs can be paused, edited, restarted. The rules we think are laws of physics could just be the parameters of the simulation. Change the code and you change the rules. The simulators might be able to reach in and tweak things. Miracles, paranormal events, glitches in reality, all of that could be explained as the simulators making adjustments or the program running into bugs. Other people find the argument horrifying. If we're simulated, then nothing we do matters in any ultimate sense. We're puppets. Our choices are scripted. Our lives are entertainment or data points for beings we can't see or interact with. Free will, if it exists at all, is an illusion coded into the software to make the simulation feel authentic. You think you're making decisions, but the outcome was determined the moment the program started running. Every moment of your life, every thought you've ever had, is the output of an algorithm. You are not a person. You are a process. Bostrom himself doesn't endorse either reaction. He's interested in the logic, not the emotional implications, but the implications are hard to ignore. If the hypothesis is true, the biggest questions in philosophy, questions about meaning and purpose and consciousness, get reframed. You're not asking, what's the nature of reality? You're asking, what were the design choices of the simulators? You're not asking whether the universe has a purpose. You're asking what the simulators wanted when they wrote the code. Every mystery becomes a question about the intentions of beings outside the system. That's a very different kind of inquiry. So is there any evidence, anything that might suggest we're in a simulation rather than base reality? The honest answer is no, not in the way evidence usually works. But there are things people point to, anomalies, features of the universe that look a little too convenient or a little too strange to be accidents. None of them are smoking guns. All of them have conventional explanations. but if you're inclined to take the simulation hypothesis seriously, you can interpret them as hints. Start with the speed of light. It's a hard limit. Nothing can move faster than light through space. Information can't propagate faster than light. There's no physical reason the universe had to work that way. Einstein's equations allow for faster-than-light travel under certain conditions, like wormholes or warp drives, but those require exotic matter or energy densities we've never observed. The universe we actually live in has a speed limit. Why? One answer is that it's a fundamental property of spacetime. Another answer is that it's a computational constraint. If the universe is being calculated, there's a maximum rate at which information can be processed and updated. The speed of light isn't a law of physics, it's the refresh rate of the simulation. Information can't travel faster than light because the system can't compute updates faster than that. Then there's the Planck length, 10 to the negative 35 meters. Smaller than that and the concept of distance stops making sense. Space itself becomes grainy, pixelated. General relativity and quantum mechanics both break down at that scale. Physicists expect that a theory of quantum gravity will show that spacetime has some kind of discrete structure at the Planck scale. Continuous smooth space is an approximation that works at larger scales, but zoom in far enough and you hit a limit. If you're a programmer, that sounds familiar. It sounds like resolution. The universe has a minimum pixel size. You can't zoom in past the Planck length because that's where the grid stops. Below that, there's nothing to render because the simulation doesn't have enough memory to store information at that level of detail. Quantum mechanics itself has features that look suspiciously like shortcuts a programmer would use to save resources. The universe doesn't seem to calculate the properties of particles until someone measures them. Before measurement, particles exist in superpositions, undefined states that collapse into definite values only when observed. That's one interpretation of quantum mechanics, the Copenhagen interpretation, and it's been the dominant view for most of the past century. Why would the universe work that way? Because calculating every particle's state at every moment would require an absurd amount of processing power. It's more efficient to leave things undefined until an observer forces the system to commit to a value. Render on demand. Don't waste computation on things nobody's looking at. Entanglement is another feature that looks odd from a programmer's perspective. Two particles can be entangled such that measuring one instantly affects the state of the other, no matter how far apart they are. The correlation is instantaneous. Faster than light. Einstein hated this. He called it spooky action at a distance, but the experiments confirm it. Entangled particles are connected in a way that doesn't fit neatly into the picture of space as a collection of separate locations. If you think of the universe as a simulation, entanglement makes more sense. The particles aren't objects separated by distance. They're variables in the same data structure. Changing one updates the other because they're stored together in memory. The appearance of spatial separation is part of the interface, but under the hood they're linked. None of this is proof. Physicists have explanations for all of these features that don't require simulations. The speed of light is a consequence of the geometry of spacetime. The Planck length is where quantum effects of gravity become important. Quantum superposition and entanglement are properties of the wave function, not glitches in a program. The conventional explanations work. They're mathematically rigorous and consistent with observation. The simulation hypothesis offers an alternative interpretation, but it doesn't offer new predictions. It's a different way of thinking about the same phenomena. The other category of potential evidence involves anomalies, things that don't quite fit the standard models. We've talked about some of them already. The Hubble tension, the impossibly early galaxies Webb is finding, dark flow, the fine-tuning of the constants. Each of these could be a sign that the simulation has edge cases the designers didn't fully account for. Or they could be signs that our models are incomplete. The difference is that incomplete models can be fixed with better physics. If we're in a simulation, the anomalies might not go away no matter how much better our theories get because they're features of the code, not the physics. Cosmic rays offer another strange case. Ultra-high-energy cosmic rays, particles that hit the Earth's atmosphere with energies far beyond what any particle accelerator can produce, seem to come from random directions in space. Their energies are so high that they shouldn't be able to travel very far before interacting with the cosmic microwave background and losing energy, and yet they reach us. Where are they coming from? Nobody knows. One explanation is that there are sources in the universe we haven't identified yet. Another explanation, if you're willing to entertain it, is that they're errors. Particles spawned by the simulation at the wrong energy because the random number generator that controls cosmic ray production occasionally spits out values outside the expected range. A bug, a glitch, the universe hiccuping. That explanation is not taken seriously by physicists, but it illustrates the problem with the simulation hypothesis. Any anomaly can be interpreted as a glitch if you want to. Any pattern can be interpreted as intentional design. The hypothesis is flexible enough to accommodate any observation. That makes it unfalsifiable. And unfalsifiable hypotheses, no matter how interesting they are philosophically, are not science. So who would be running the simulation? The most common answer is that it's a post-human civilization from our future. Humans, or our descendants, or whatever we evolve into, eventually reach a level of technology where we can simulate entire universes. We run ancestor simulations to study our own history. We're living in one of those simulations. The people running it are us, just billions of years more advanced. They're studying the early 21st century the way we study ancient Rome, by recreating it in detail and watching what happens. Another possibility is that the simulators are an entirely different species, not human, not even from our universe. They exist in a higher level reality that has completely different physics. They built a computer or something analogous to a computer, and they're running our universe as an experiment. Maybe they're testing different sets of physical laws to see which ones produce interesting outcomes. Maybe they're running billions of universes in parallel, each with slight variations, and comparing the results. We're in one of those test cases. The simulators have no connection to us. They might not even know we're here. We could be an unintended byproduct of the simulation, emergent complexity that arose from the rules they programmed in. They were looking for something else, and we happened. A darker possibility is that the simulation is punishment or entertainment. We're characters in a game or a story. The simulators are watching us struggle and suffer, and that's the point. This version of the hypothesis leans toward theological territory. If the simulators have that much control over our reality, they're functionally gods. And if they're gods, the question of why they built the universe the way they did, with all its suffering and randomness and cruelty, is just the problem of evil rephrased in technological terms. Bostrom's paper doesn't speculate much about the motivations of the simulators. He focuses on the probability argument, but motivations matter if you're trying to take the hypothesis seriously. If we're in a simulation, understanding the purpose of the simulation tells you what kind of reality you're living in. Are we science? Are we entertainment? Are we art? Are we a mistake? Each answer leads to a different set of implications. Elon Musk has said publicly that he thinks the odds we're living in base reality are 1 in billions. He's not a philosopher, he's an engineer, but he's taken the simulation hypothesis seriously enough to talk about it in interviews. His reasoning follows Bostrom's logic. Video games are getting more realistic every year. Virtual reality is improving. If that trend continues, Eventually, we'll be able to create simulations indistinguishable from reality. Once that happens, the number of simulated realities will dwarf the number of base realities. Therefore, we're probably in a simulation. Musk has also joked, or maybe not joked, that he hopes the simulation doesn't get turned off. Other physicists and philosophers push back. They argue that consciousness might not be simulable. Maybe there's something about subjective experience, the qualia of what it's like to be you, that can't be replicated in software. If consciousness requires something beyond computation, something tied to the specific physical substrate of biological brains, then you can't create conscious beings in a simulation. You can create entities that behave as if they're conscious, but there's no one home. They're philosophical zombies. And if that's the case, the simulation hypothesis collapses because the simulators aren't creating observers, they're creating puppets. And we're not puppets, we're observers. Therefore, we're not in a simulation. That argument hinges on assumptions about consciousness that are themselves unproven. Nobody knows whether consciousness is substrate independent. The brain is made of atoms following physical laws. If you replicate those laws in a computer, why wouldn't you get the same result? Saying that consciousness requires a biological brain is a claim that needs evidence, and so far there's no evidence either way. Another objection is computational. Simulating an entire universe in detail requires an unimaginable amount of processing power. Every particle, every interaction, every quantum event, the simulators would need a computer larger than the universe they're simulating. That's a problem. Where do they get the resources? One answer is that they don't simulate everything. They only simulate what's being observed. The rest of the universe exists in a low-resolution state, a simplified model that gets filled in with detail only when someone looks. That's the render-on-demand approach. It saves resources, but it introduces the risk of inconsistencies. If two observers look at the same region from different angles or at different times, the simulation has to make sure the details match. One slip and the illusion breaks. The other answer is that the simulator's reality has more resources than ours. Maybe their universe is bigger. Maybe their physics allows for more efficient computation. Maybe they're running our simulation on a computer the size of a galaxy in their world, and that's trivial for them. If the base reality is vastly larger or more energy-rich than our simulated reality, the resource problem goes away. But now you're stacking assumptions. Advanced civilization, check. Ability to simulate consciousness, check. Vastly larger base reality, check. Each assumption makes the hypothesis less likely, not more. The philosophical implications cut deep. If the simulation hypothesis is true, free will becomes a technical question. Are the simulators running a deterministic program where every outcome is pre-calculated, or are they using random number generators to introduce unpredictability? If it's deterministic, you don't have free will. Your choices are already encoded in the initial conditions of the simulation. If it's probabilistic, you have something like free will, but only in the sense that a dice roll is free. The outcome isn't fixed, but it's not controlled by you either. It's controlled by the random number generator. Either way, the sense that you're making meaningful choices is an illusion. Purpose becomes another casualty. If we're in a simulation, the purpose of the universe is whatever the simulators intended, not what we think it is, not what religion or philosophy tells us. The simulators wrote the program for a reason, and that reason might have nothing to do with us. We could be incidental, background characters in a simulation designed to study something entirely different, or we could be the main event, the whole point. The simulators might care deeply about what we do and how we develop. There's no way to know. The purpose of the simulation is hidden from us, the same way the code is hidden. Even the nature of reality shifts. If we're simulated, then the physical universe, the atoms and forces and spacetime, is not fundamental. It's a construct, a user interface. The real reality, the base layer, is the hardware the simulators are using and the laws that govern their world. Our physics is just the rules of the program they wrote. Change the code, change the physics. There's no guarantee that the physics of base reality looks anything like ours. It could be completely alien. Our universe could be running on principles that don't even involve space or time in any recognizable form. That realization is either liberating or terrifying, depending on your temperament. Liberating because it means the universe is less constrained than it appears. If it's a program, it can be reprogrammed. Death might not be final. Suffering might be a bug that gets patched in the next version. The simulators might have backups. They might run the simulation multiple times with different parameters. Your life might not be unique, but it might be repeatable. Or terrifying because it means nothing you experience is grounded in anything solid. The atoms you're made of aren't real. The stars you see at night aren't real. The people you love aren't real in the sense you thought they were. Everything is data, and data can be deleted. The simulation hypothesis doesn't answer the biggest questions, it just reframes them. Instead of asking, why does the universe exist, you ask, why did the simulators create the simulation? Instead of asking what happens after death, you ask what happens when the program stops running. Instead of asking whether life has meaning, you ask whether the simulators care about your experience. All the hard questions get pushed one level up, out of reach. You're left in the same place you started, except now there's an additional layer of uncertainty between you and any possible answers. And yet the hypothesis won't go away. It keeps coming up in conversations, in papers, in interviews with physicists and philosophers and tech entrepreneurs. Not because there's evidence, there isn't, but because it's hard to rule out. The logic is clean, the implications are profound. And the possibility, however remote, that we're living inside a construct built by beings vastly smarter and more powerful than us, forces a kind of humility. Maybe the universe we see is real, maybe it's not. Either way, we're stuck inside it, trying to make sense of patterns and anomalies and mysteries that might not have answers, or might have answers we're not capable of understanding, or might have answers that exist somewhere outside the system, in a place we can't reach and can't see. So are we code? Probably not. The simulation hypothesis is fascinating as a thought experiment. It's lousy as a scientific theory because it doesn't make testable predictions. It's a placeholder for our uncertainty, a way of acknowledging that the universe could be stranger than we're prepared to accept. If we are in a simulation, we'll likely never know for sure. The simulators, if they're competent, won't leave obvious clues lying around. They'll design the system to be self-consistent. Any test we run will confirm that the simulation looks exactly like a real universe. And if we're not in a simulation, then the question was always moot. Either way, the universe we experience is the only universe we have access to. It's the reality we're embedded in, simulated or not, it's home. And the mysteries we've been talking about, the horizons and dimensions and flows and structures, they're still there, still demanding explanation. Whether the explanation is physics or programming doesn't change the fact that we don't have it yet. We're still standing at the edge of what we know, looking out at an enormous unknown, trying to figure out what comes next, trying to figure out what it all means. And that question, the question of meaning, is where this whole journey has been heading. Because once you've stared at the edge of the observable universe long enough, once you've considered the multiverse and the extra dimensions and the possibility that none of it is even real, you're left with one final uncomfortable truth. The universe doesn't care whether you understand it or not. It's going to keep expanding, keep flowing, keep hiding most of itself behind horizons you can't cross. The question is what you do with that. How you live in a universe that's too big to see and too strange to fully comprehend. And that's the part we need to talk about next. And that question, the question of meaning, is where this whole journey has been heading. Because once you've stared at the edge of the observable universe long enough, once you've considered the multiverse and the extra dimensions and the possibility that none of it is even real, you're left with one final uncomfortable truth. The universe doesn't care whether you understand it or not. It's going to keep expanding, keep flowing, keep hiding most of itself behind horizons you can't cross. The question is what you do with that. How you live in a universe that's too big to see and too strange to fully comprehend. And that's the part we need to talk about now. Let's start by recounting what we've been dealing with. Because when you lay it all out in sequence, the scale of the disturbance becomes clear. Each theory we've explored doesn't just add information, it strips away a layer of certainty. It takes something you thought was solid and reveals that it was standing on nothing. The observable universe is 93 billion light-years across. That's the first boundary. Everything we can see, every galaxy, every star, every photon that has reached us since the beginning of time is contained within that sphere. And we know, with reasonable confidence, that the sphere is not everything. Space continues beyond the horizon. The universe keeps going. How far, we don't know. Maybe it's finite but much larger than what we can observe. Maybe it's infinite. Either answer is uncomfortable. If it's finite, what's at the edge? If it's infinite, how did infinity begin? The question doesn't resolve, it just shifts. Then we talked about true nothingness, not empty space, not a vacuum with quantum fluctuations. True nothingness, the absence of space, time, matter, energy, fields, laws, dimensions, the absence of the framework that allows anything to be absent. That's the version of beyond that most people's brains refuse to process, because nothing in your experience prepares you for it. You've seen empty rooms, you've felt silence, you've looked at a blank page, but none of those are nothing. They're all something. The room has air, the silence has duration, the page has paper. True nothingness is the absence of the room, the duration and the paper. It's the absence of the possibility that any of those could exist. And the disturbing part is that if the universe has a boundary, that's what's on the other side. Not darkness, not void, just the end of everything that is. Some physicists argue that true nothingness is impossible, that quantum mechanics or logic or the structure of reality itself prevents it from existing. If that's right, then existence is mandatory. There has to be something, always, because the alternative is unstable or incoherent. And if existence is mandatory, then the universe or the multiverse, or whatever the largest structure is, has no beginning and no end. It just is, forever. That trades one kind of discomfort for another. You're no longer worried about nothingness. You're worried about eternity. An existence that never started and will never finish. No creator, no purpose, no reason. Just an infinite, self-sustaining structure that exists because the alternative is logically impossible. That's not comforting, that's just a different flavor of vertigo. Then there's the multiverse, multiple versions, all with their own implications. The inflationary multiverse, where eternal inflation spawns an endless tree of bubble universes, each with its own Big Bang, each isolated from the others by space expanding faster than light. The string landscape, where 10 to the power of 500 different vacuum states produce 10 to the power of 500 different universes, each with different laws and constants. The many worlds interpretation, where every quantum event splits reality into branches, generating an unimaginably large number of parallel timelines, all as real as this one, all happening simultaneously in a superposition you can't perceive. And the brain world scenario, where our three-dimensional universe is a membrane floating in a higher dimensional space, possibly surrounded by other brains, other universes, separated by gaps we can't cross. Each version of the multiverse shrinks the significance of what we can see. The observable universe stops being the universe. It becomes one bubble, one vacuum state, one branch, one brain. And the totality of existence becomes something vastly larger and more complex than anything we evolved to comprehend. The anthropic principle kicks in. We're in this universe because this is the kind of universe where observers can exist. The other universes are still there. We just don't see them because we're not in them. The fine-tuning of the constants isn't evidence of design. It's evidence of a large sample size. Roll the dice 10 to the 500 times, and eventually you get a universe that looks like ours. We're the result of statistics, not intention. That realization, if you sit with it, is destabilizing. For most of history, humans assumed they were at the center of something meaningful. The Earth was the center of the cosmos. Then it wasn't, but at least we were in the solar system that mattered. Then the solar system turned out to be ordinary, but at least the Milky Way was significant. Then the Milky Way became one galaxy among billions, then billions became trillions. And now, with the multiverse, even the universe we live in stops being special. It's one instance in a set so large that calling it infinite might be underselling it. You are not at the center. You are not in a privileged location. You are not even looking at a representative sample of reality. You're in a bubble, on a branch, on a brain, seeing a narrow slice of something incomprehensibly larger, and the rest of it doesn't know you exist and never will. Then we added extra dimensions, the idea that the three spatial dimensions we experience are not all there is, that at every point in space, there are additional dimensions curled up so small we can't see them, or not curled up at all, large dimensions that we can't access because we're confined to a brain, a three-dimensional surface embedded in a higher dimensional bulk. Gravity leaks into those dimensions. That's why it's so weak compared to the other forces. The other forces are stuck on the brain with us. Gravity spreads out into the extra dimensions and gets diluted. If that's true, then the universe we experience is a projection, a shadow, a lower dimensional slice of a higher dimensional object we can't visualize because our brains don't have the hardware for it. And the full structure, the real shape of reality, is hidden from us not because it's far away, but because it's in directions we don't have words for. Directions perpendicular to all three spatial dimensions simultaneously. You can't point to them, you can't imagine them, you can only describe them mathematically and trust that the math is pointing at something real. The holographic principle takes that even further. It says that all the information in a volume of space can be encoded on the boundary of that volume. The three-dimensional universe we see might be a holographic projection of information stored on a two-dimensional surface at the edge of the cosmos. In that view, space itself is not fundamental, it's emergent, a derived property of something simpler that lives in fewer dimensions. If that's correct, then the dimensions we experience, the ones we base our entire understanding of reality on, are illusions. Useful illusions, but illusions nonetheless. The deeper structure is something else entirely, and we're seeing a flattened version of it, like watching a hologram and mistaking the projection for the object. Then there's dark flow. The observation, still contested but not dismissed, that hundreds of galaxy clusters are moving in a coherent direction, streaming toward a region of space that shouldn't be pulling them. If the flow is real, It suggests that something beyond our cosmic horizon is massive enough to tug on structures billions of light years across. We can't see what's pulling us because its light hasn't reached us yet, but its gravity has. That means the observable universe is not dynamically isolated. We're part of a larger structure, and that structure is influencing us in ways we can measure but can't explain. The universe beyond the horizon isn't just more of the same. It's structured. It has concentrations of mass or energy large enough to produce effects we can detect from inside our bubble. We're not alone, cosmologically speaking. We're embedded in something bigger, and that something is pulling us toward it. Where we're going, we don't know. What's there, we can't see. But the current is real, and we're in it. And then, as if all of that wasn't enough, there's the simulation hypothesis. The idea that the universe isn't made of matter and energy at all. It's made of information, code, a program running on hardware that exists in some higher-level reality. Every particle, every force, every dimension, all of it is computed, rendered, executed by a system vastly more advanced than anything we've built. You are not a biological organism. You are a process, a subroutine. The universe isn't a thing, it's a calculation. And the most disturbing part is that if the hypothesis is true, you will never know for sure, because any test you run to check whether you're in a simulation is itself part of the simulation. The evidence you collect, the logic you use, the consciousness you experience, all of it could be generated by the system you're trying to test. You're trapped inside. There's no way out, no way to see the code from the inside. The best you can do is notice anomalies, patterns that look like shortcuts or bugs, and wonder whether they're evidence of a program or just features of physics you don't understand yet. So here's where we are. The observable universe is too small. The actual universe is too big. The multiverse is too strange. The extra dimensions are too hidden. The dark flow is too unexplained. And the simulation hypothesis is too unfalsifiable. Every theory we've explored takes something away from the picture of reality you grew up with. The Earth is not the center. The Sun is not the center. The galaxy is not special. The universe is not unique. Space is not fundamental. Time might not be either, and the whole structure might be running on a computer you can't access. Layer by layer, the ground falls away. What you thought was solid turns out to be contingent, provisional, possibly illusory. And the deeper you look, the less stable it gets. Now let's talk about what that does to us. Not as a species, as individuals. What does it do to you to realize that the universe you live in is probably not all there is, that the reality you experience is a narrow slice of something vastly larger and stranger, that the constants and laws you thought were universal might be local, that the dimensions you move through might be projections, that the significance you assumed came with being a conscious observer might be a statistical accident? What does it do to you to sit with that? For some people it does nothing. They hear the theories, nod along, and go back to their lives. The universe is big, fine. It's always been big. Knowing it's bigger doesn't change the fact that you have to pay rent and feed the dog and show up to work on Monday. The abstract doesn't touch the concrete. The cosmic doesn't interfere with the mundane. Life goes on. For other people, it's destabilizing. Not in a dramatic way, not in a way that makes them quit their jobs or join a monastery or spiral into existential despair. Just a quiet, persistent sense that something has shifted. The world looks the same, but it doesn't feel the same. You walk outside and look at the sky, and you know, in a way you didn't before, that the stars you're seeing are a tiny fraction of what's out there. That most of the universe is hidden behind a horizon you can't cross. That the light reaching your eyes left those stars thousands or millions of years ago, and the stars themselves might not even exist anymore. that the space between you and them is expanding, pulling them farther away every second, and eventually they'll cross a threshold and disappear forever, carried beyond the reach of light by the accelerating expansion of the cosmos. You knew all of that intellectually before, but now you feel it. And once you feel it, you can't unfeel it. That's the vertigo. The sense that the ground beneath your feet is thinner than you thought. That reality is larger and stranger and less stable than your intuition prepared you for. That the universe doesn't care about you, not because it's hostile, but because it's indifferent. It doesn't even register your existence. You're a pattern in the data, a fluctuation in a field, a temporary arrangement of particles that will dissolve back into the background in a cosmically insignificant amount of time. The stars will keep burning. The galaxies will keep drifting apart, the universe will keep expanding, and none of it will notice that you were here. Some people find that freeing. If nothing matters on a cosmic scale, then nothing you do is cosmically important, which means you're free to define your own meaning. The universe doesn't hand you a purpose, you create one. You decide what's worth caring about. You choose how to spend the brief flicker of time you have. That's a kind of freedom, a radical freedom. No script, no destiny, no preordained role. Just you standing in a vast, indifferent universe, making choices that matter to you even though they don't matter to the cosmos. Other people find it crushing. If nothing matters on a cosmic scale, then nothing matters, period. The love you feel, the work you do, the relationships you build, all of it is temporary and ultimately meaningless. The universe will erase it, time will smooth it out. In 1 trillion years, the stars will have burned out. In 1 trillion years, even the black holes will evaporate. The universe will be cold, dark, empty, and nothing you did will have left a trace. You're not building towards something. You're just filling time before the inevitable dissolution. That's not freedom, that's futility. Both reactions are understandable, neither is wrong. The universe doesn't pick sides, it just is. How you respond to that is up to you. But there's a third reaction that's harder to name. It's not despair, and it's not liberation. It's something closer to awe, not the comfortable awe you feel when you see a beautiful sunset or a mountain range. The other kind, the kind that makes you feel small and strange and slightly afraid. The kind that comes from realizing you're standing on a rock orbiting a star in a galaxy that's one of trillions, and the whole visible universe is just a bubble inside something unimaginably larger, and you have no idea what that larger thing is or whether it's even a thing at all. The kind of awe that doesn't give you answers. It just expands the space where questions live. That awe is what keeps people looking up. Not because they expect to find comfort, because they can't stop wondering. What's out there? What's beyond the horizon? What's in the extra dimensions? What's pulling the galaxy clusters? What's running the simulation, if there is one? What does true nothingness even mean? The questions don't have answers yet. They might never have answers. But the asking is what makes us human. The refusal to look away. The insistence on trying to understand, even when the understanding keeps slipping out of reach. And that brings us to the core of the disturbance. The thing that ties all these theories together, the reason they're unsettling, isn't just that they make the universe bigger or stranger, it's that they challenge the basic assumption that the universe is knowable. That with enough time and enough data and enough cleverness, we can figure it out. That reality has a structure we can map, and laws we can derive, and a history we can reconstruct. Most of science rests on that assumption. The assumption that the universe makes sense, that it follows rules, that those rules are consistent and discoverable. These theories don't overturn that assumption directly, but they complicate it. If the universe is one bubble in an eternal multiverse, then the rules we've discovered are local. They apply here, but not everywhere. Other bubbles have other rules. There's no universal set of laws, just a landscape of possibilities. If extra dimensions exist and we can't access them, then the structure of reality includes regions we can't map, hidden dimensions, hidden forces, hidden matter. The universe is bigger than what we can observe, and the hidden part might be vastly larger than the visible part. If the simulation hypothesis is true, then the rules we've discovered aren't fundamental. They're the parameters of a program. Change the code and you change the rules. The universe doesn't make sense on its own terms. It makes sense in terms of the system running it. And we don't have access to that system. So the most disturbing theory isn't one specific idea. It's the pattern that emerges when you look at all of them together. The pattern is this: reality is not what it looks like. The universe you experience is a narrow slice of something larger, and the larger thing is hidden from you by horizons you can't cross, dimensions you can't access, and possibly by the structure of the simulation itself. You are embedded in a reality you cannot fully observe, governed by rules you cannot fully derive, moving through a space you cannot fully map. And the most you can do is collect data from the narrow window you have access to and try to extrapolate what's beyond the frame. That's the real disturbance. Not that the universe is big, not that it's strange, but that it might be fundamentally incomplete from your perspective. That there are truths you can never verify because they exist outside the boundary of what's observable. Truths about what lies beyond the cosmic horizon. Truths about the shape of the extra dimensions. Truths about whether other universes exist. Truths about whether you're in a simulation. Truths about what, if anything, came before the Big Bang. Truths about what true nothingness actually is, or whether it can exist at all. The universe is full of questions that might not have answers you can reach. Not because you're not smart enough, not because the technology isn't good enough, but because the questions are about regions of reality that are structurally inaccessible from where you're standing. That's the vertigo, the sense that the more you learn, the more you realize how much is hidden. The observable universe is like a room with no windows. You can study everything inside the room in exquisite detail. You can measure the walls, the floor, the ceiling. You can catalogue every object, every particle, every photon. But you can't see outside, and the thing outside might be vastly larger than the room. It might be a building, it might be a city, it might be an infinite landscape, or it might be nothing. And you'll never know because the walls don't have windows and you can't walk through them. Some people react to that by saying, "Fine, then we focus on the room. The room is what we have access to. The room is what we can study. Let's understand the room as completely as possible and stop worrying about what's outside." That's a pragmatic response. It's also the response that most working scientists take. They focus on the questions they can answer with the data they can collect. The rest is speculation. Interesting speculation maybe, but not science. Other people react by saying, "No, we keep asking, we keep pushing at the boundaries, we keep building better telescopes, better detectors, better theories. Maybe we find a way to probe the extra dimensions. Maybe we detect a signal from another brain. Maybe we find a glitch in the simulation. Maybe we figure out what's pulling the galaxy clusters and it tells us something about what's beyond the horizon. Maybe we can't see outside the room, but we can listen. We can measure how the walls shake when something on the other side moves. We can collect indirect evidence and build models and test those models and refine them. We can't leave the room, but we can learn about what's outside by studying how the outside influences the inside. That's the approach that drives theoretical physics and cosmology. It's speculative, it's tentative, but it's not empty speculation. It's constrained by math and observation. It's the best we can do, and maybe that's enough. Maybe the fact that we can ask the questions, even if we can't answer all of them, is what matters. Humans have been asking what's beyond the horizon since the first time someone stood on a hill and looked out at the edge of the visible world and wondered what came next. We've been doing it for thousands of years, and every time we thought we'd reached the final boundary, we found another one. The edge of the village became the edge of the known world. The edge of the known world became the edge of the planet. The edge of the planet became the edge of the solar system. The edge of the solar system became the edge of the galaxy. The edge of the galaxy became the edge of the observable universe. And now we're standing at that edge, looking out and realizing that the observable universe is just another boundary. Not the final one, just the latest. The pattern suggests that there will always be another boundary, that the quest to understand what's beyond will never end because beyond is not a place, it's a condition. It's the edge of what you can see from where you're standing. Move forward and the edge moves with you. New regions come into view, old regions slip behind the horizon. The boundary shifts, but it never disappears. There's always something farther out, something hidden, something you can't quite reach. That might sound like a condemnation, an infinite treadmill. You'll never finish, you'll never see it all, you'll never have the complete picture. But maybe that's not a failure. Maybe that's just the nature of being a finite observer in an infinite or near-infinite reality. You don't get the whole picture, you get a piece, a slice, a window, and the fact that the window is narrow doesn't make what you see through it meaningless. It makes it precious, because it's all you have. The observable universe, the data you can collect, the models you can build, the questions you can ask, that's your piece of the puzzle. It's a small piece, it's an incomplete piece, but it's yours. And here's the thing, the theories we've been talking about, the ones that strip away certainty and expand the boundaries and make the universe stranger and less knowable, they're not nihilistic. They're not saying nothing matters. They're saying the universe is bigger and more complex than you thought, and that makes the part you can see more remarkable, not less. The fact that you, a temporary arrangement of particles on a small planet in an unremarkable galaxy in one bubble of an eternal multiverse, can sit down with a piece of paper and some equations and figure out that the universe is expanding, that it had a beginning, that it's full of structures you can't see but can infer, that it might be embedded in extra dimensions or running on a simulation or surrounded by other universes. The fact that you can do that with a brain that evolved to hunt and gather and avoid predators is extraordinary. It's one of the most extraordinary things that has ever happened in the history of the cosmos. A tiny part of the universe figuring out the larger structure it's embedded in, matter becoming aware of itself, the universe looking at itself and asking what it is. That doesn't make you the center of anything. It doesn't give you cosmic importance, but it does mean you're participating in something real. The search for understanding, the attempt to map the edges of the knowable, the willingness to stand at the boundary and look out at the unknown and ask what's there, even when the answer might be nothing or everything or something so strange that the question stops making sense. So what's the most disturbing theory? It depends on what disturbs you. If you're disturbed by the idea that existence itself might not be necessary, that true nothingness could be the default state and the universe is a temporary deviation from it, then the void is the most disturbing. If you're disturbed by the idea that your universe is not unique, that the laws and constants you thought were universal are just one random draw from an infinite set, then the multiverse is the most disturbing. If you're disturbed by the idea that there are dimensions of reality you can't access, directions you can't point to, structures you can't see, then the extra dimensions are the most disturbing. If you're disturbed by the idea that something beyond the observable universe is pulling you toward it and you don't know what it is, then the dark flow is the most disturbing. And if you're disturbed by the idea that none of this is real, that the universe is a simulation and you're a process running inside it, then the simulation hypothesis is the most disturbing. But the truly disturbing thing, the one that sits underneath all the others, is the realization that you might never know which theory is correct, that the answer might be hidden behind a boundary you can't cross. That reality might be fundamentally incomplete from your perspective, and no amount of data or cleverness or time will change that. The most disturbing thing is the possibility that the universe is knowable but not fully knowable, that there are questions you can ask but never answer, that the search for understanding is endless not because you're bad at it, but because the structure of reality itself puts some truths out of reach. And yet, knowing that, we keep looking, we keep building telescopes, we keep writing equations, we keep asking what's beyond the horizon. Not because we think we'll finish, but because the asking is what we do. It's what we've always done. It's what makes us human. The refusal to accept that the boundary is final, the insistence on pushing at the edges, the willingness to stand at the edge of the knowable and stare into the unknown and say, I wonder what's there. That's where the journey ends or doesn't end. The observable universe is 93 billion light-years across. Beyond that, the theories multiply. Nothingness, multiverse, extra dimensions, dark flow, simulation, each one a possibility, each one disturbing in its own way, none of them proven, none of them ruled out, and all of them pointing to the same conclusion. The universe is stranger than you thought, reality is larger than you can see, and the search for what's beyond will never be finished, because beyond keeps moving. The horizon shifts, the questions multiply, the mysteries deepen, and we're still here, standing on a small rock in a vast cosmos, looking up, asking what comes next, knowing we might never get the full answer, knowing we have to keep asking anyway, because that's what we are, curious, persistent, stubborn enough to ask questions that might not have answers, brave enough to look at a universe that doesn't care whether we understand it and try to understand it anyway. That's the unspeakable truth. Not that the universe is too big or too strange, but that it's exactly big enough and exactly strange enough to keep us wondering forever. And maybe that's not a curse, maybe that's the point. So here we are, standing at the edge of everything we can see, staring into an abyss that might be infinite, or might be nothing, or might be something so strange that the words we use to describe it break down before they get close. The observable universe is 93 billion light-years across. Beyond that, we have theories, elegant ones, terrifying ones, ones that make the ground feel less solid than it did when you woke up this morning. And not one of them gives you the comfort of certainty. That's the real answer if there is one. Not what's beyond, but that beyond exists. That the universe you experience is a window, not a room. That reality is larger and deeper and more layered than your senses can reach. That every boundary we've ever found, from the horizon of the visible Earth to the edge of the solar system to the cosmic horizon itself, was just another frame, another limit, another place where the map runs out and the blank space begins. We've spent millennia trying to fill in that blank space. We've built better instruments, written better equations, trained ourselves to think about things our brains were never designed to visualize, extra dimensions, parallel universes, flows that shouldn't exist, simulations we can't escape, and every answer we find opens 10 more questions. The search doesn't end, it compounds. Maybe that's not a flaw, maybe that's the design. A universe structured in such a way that no matter how far you look, there's always something farther. A reality that refuses